Good afternoon, all.
Good afternoon, Yogesh. So, a very good afternoon to all participants, and welcome to the sixth day, the final day AICTE ATAL FDP on future perspective of AI and data sciences. Just a minute. Maybe noise from other side. Fine. Okay. So for this session, we have with us Professor Yogesh Simmhan as the guest speaker. Before he starts his talk, let me take the privilege to introduce him. Professor Yogesh Simmhan is an associate professor in Department of Computational Data Sciences at Indian Institute of Science, Bangalore, and a Swarna Jayanti professor. His research focuses on the scalable software platforms, algorithms, and applications on distributed systems, particularly on cloud and edge computing, temporal graph processing, and scalable machine learning to support big data and Internet Things applications. With over 100 peer-reviewed papers to his name, Dr. Simmhan has received the Best Paper Award at IEEE International Conference in Cloud Computing 2019. The IEEE TCSC Scale Challenged Award in 2019 and 2012 consecutively. The Distinguished Paper Award for the Europar 2018 and IEEE ASIM Supercomputer HPC Storage Challenge Award 2008. In 2020, he was honored with the IEEE TCSC Award for Excellent Scalable Computing for Mid-Career Researchers. He serves as the Associate Editor-Chief of Journal of Parallel and Distributed Systems, that is JPDC, and the Associate Editor of, for Future Generation Computing Systems, FGCS. He has also served as an Associate Editor of IEEE Transactions and Cloud Computing and contributed to the IEEE Future Direction Initiative to Big Data. Professor Simmhan holds PhD Computer Science from Indian University, Bloomington, before he joined IISc. He is Research Assistant Professor at University of South Carolina, California, USC, then Los Angeles, and postdoctoral research at Microsoft Research and San Francisco. He has distributed members of ACM, as distinguished contributor to IEEE Computer Science Society, and members of ACM India Executive Council. With this small brief introduction, I would like to hand over the session to the Professor Yogesh.
Thank you so much, Nachiket. Really appreciate it. Let me quickly share my screen, if that's okay.
No.
Okay, hopefully my screen is visible.
Not, yeah, it's appearing. Yeah, it's appeared.
Okay, great, thank you. First of all, apologies that I could not start the talk at my scheduled time. There's a sudden summons from PST to present some project proposal that we had sent between 2 to 3. So sorry about that, but hopefully we'll make up for it in terms of the engagement today. And a big thank you to Nachiket and his team at IIITDM in Kancheepuram for conducting this FDP. I saw the program; it looked very, very interesting. So hopefully all of you are have gained a lot of knowledge in the last few days, and you're on the last day, I believe, and hopefully I can add on to what you've learned. I'll talk about federated learning on edge accelerators today, and do sort of, if there's a way to raise your hand or sort of post questions and so on, do that. I'd be more than happy to answer questions as well as part of this, because the point is to learn in this process, right? But before I start, for those who might not know IISc as well, so we are we are the top university in India. We're one of the older universities set up in 1909, and we are a truly interdisciplinary institute, right? So we have departments both in engineering as well as the sciences, which makes for a very interesting mix of work that goes on. And this also means that you're able to have interdisciplinary centers such as on nanotechnology, brain and computing, robotics and quantum, all of which require people from different domains to work together. The department I'm part of, computational data sciences, itself is an interdisciplinary department. We have faculty like myself who have a computer science degree. We have engineers, we have people even from biological sciences who are part of this. And we primarily work at the intersection of systems, methods, and applications, right? So I myself am I'm a computer systems researcher, working on things like cloud and edge computing, as I'll talk about. We have other faculty working on HPC as well. We also have methods in terms of computational methods or data science methods where faculty work on, as well as people from the application side, right, who are part of this. And as you know, IISc is predominantly a postgraduate institution, so most of our students are PhDs and master's students. The work I do in my own group, we call ourselves a Dream Lab, looks at how you can make use of the plethora of computing hardware that's out there, starting from your more by now it's almost commonplace cloud computing systems to more recent innovations such as containers, as well as things like edge devices and edge accelerators, and to some extent even quantum computing that's around the horizon. So that's all the hardware devices that are out there. And all these are typically, it's not just working on a single hardware device, but you have to work across multiple hardware devices to get things done, right? And we'll talk a lot more about that today. But in order to make use of such distributed and heterogeneous hardware devices, you need enabling layers, right, on top of that, right? So our focus is more in the middle of this stack, right, where we look at software platforms and middleware platforms that allow you to efficiently deploy applications, manage them in a reliable and a scalable manner, and get the best use of the underlying hardware. And in this regard, we work with things like functions as a service and workflow orchestration. We look at federated learning, which we'll talk about today. We have work going on around distributed graph processing platforms, and even GNN, federated and distributed GNN platforms, and even looking at software platforms for drones or fleets of drones that collaboratively work either among themselves or with even cloud backends to solve problems, right? And going up the stack, even one more layer, right? This gets into algorithms and abstractions, because it's one thing to write code directly with the hardware, underlying hardware in mind, but the better thing is to actually abstract out the hardware and have programming models that you can define. And behind the scenes, the programming model itself is converted into a distributed execution that runs across these heterogeneous systems, right? So here again, we've done a fair bit of work around abstractions for federated learning, like I'll talk about, abstractions for graph processing, abstractions for streaming graphs, and also workflows and so on, right? And lastly, the application domain comes in, and they are oftentimes a very interesting, motivating sort of motivator for the middle layers of the stack, right? So the top and the bottom are in a sense given, and the middle is where adapts to these, right? And here again, we work a lot with IoT and smart cities, in particular more recently in smart mobility. We have a big center of excellence that's starting in urban mobility. So many of the things I'm going to talk about today are actually relevant from that domain as well. There's also work that we do on things like fintech, for example, working with NPCI in some of the ways in which they do things like fraud modeling and scalability of the UPI transactions and so on. So there again, some of the work that we do with graph processing comes into play, as well as some of the work we do on distributed systems and systems design comes into play from a scalability perspective, right? So that's a big picture of some of the work in our lab. Just to give you a few examples, and this is more to give a flavor of what distributed systems research could be, because hopefully you'll see something interesting over here, and that might trigger some research or teaching that you yourself want to incorporate as part of your the work that you do. One of these is something called CrossFAS, which is a workflow orchestration on hybrid cloud. So what does this mean? If you want to use the cloud, there are many ways to do that. You can just rent a VM and run your application within the VM. You could use some kind of a proprietary framework given by the cloud provider, or you could use something like Spark or Hadoop. There are multiple ways to do that. But functions as a service has emerged recently as a very easy way of deploying, of composing and deploying an application, right? So if you just want to, if you have a small piece of logic, right? It could be, let's say, a nice ML model that you have trained and you want to make it available as a service, right? Or some kind of an algorithm that you have developed that you want to make available at scale, right? What FAS allows you to do is just take that function, maybe write it in a Python wrapper, and this Python piece of code itself can be deployed in a single step, in a single shot, very easily within the cloud. And what the cloud provider gives you, be it AWS Lambda or Azure Functions or Google Functions and so on, they take this Python functions and all its dependencies, wrap that within a container, deploy it within a container image, and when a request comes to access the service endpoint that is represented by this application, your function logic, it'll automatically spin up a container, deploy the container image on that, and have that respond to the request. Logic will be called, and you will give an answer back, right? And if you have a lot of requests coming in, maybe tens of requests per second, the cloud platform itself will create many such containers, right? So that the quality of service, the latency for responding to the request does not deteriorate, right? So that way the scale out and scale in of the containers are automatically managed by the cloud provider. So that's something that already exists. Like I said, Lambda and Azure Functions are examples of that, and OpenFaaS and OpenWhisk are examples in the private cloud space, right? What we have done is try to look at how we can make this not proprietary to a single cloud provider, right? And that's a key challenge in cloud computing in general. It's not, people don't realize it as a problem. The problem starts emerging if you decide that someday, hey, what I'm paying for Amazon AWS seems a little bit too high. Maybe I want to migrate to Azure, or I want to migrate to Google, right? At that point in time, you realize that by starting to use one cloud provider and building more and more on top of the cloud, you've built in a lot of dependencies, right? And it's not easy to lift and shift all your applications from your enterprise applications from one cloud provider to a different cloud provider, right? So what we're looking at is a way in which, if FaaS, functions as a service, is one very popular way of composing applications for the cloud, can you ensure that the FaaS applications that you compose themselves can actually be very easily shifted from one cloud provider to another provider, right? Not just that, to the extent that even if it's a single FaaS application, right, which has been composed into a workflow, right? Like you see over here, this is a workflow. The user has composed, each one is a function. The upstream function executes, passes its output to the downstream function, which executes on this as input and generates an output and so on. This is called a directed acyclic graph, or it's a data flow or a workflow programming abstraction. And if you have submitted this, what we do as part of CrossFaaS is to actually take this and actually figure out which is the right cloud platform in which each of these functions should be executing, right? And takes this DAG, splits it into smaller sub-DAGs, each of which might be running on a different cloud provider, and the CrossFaaS itself orchestrates the execution across the cloud providers, while execution within a single cloud provider is maintained natively by that particular cloud service provider, right? So that's something that we've done as part of CrossFaaS, so to make the clouds, make multi-cloud portable applications for FaaS applications more possible. The other thing is also that we recently started, this is in collaboration with IBM Research, is to see how a similar idea around FaaS could be extended to quantum computing, right? Until 2 years back, I didn't even imagine I would be working on quantum computing. It seemed too esoteric and far-fetched, and I'm not from a physics background to be able to understand what goes on in quantum computing. And even today, I don't understand the ins and outs of quantum computing, right? But to the same extent that I don't understand the ins and outs of even the CUDA core. I don't know, I'm not an architecture person, right? So, which means that I might not completely understand how a CUDA core or an AMD processes at the very lowest basic level works. That might be my architecture colleagues might understand that better, but I still use that, we still optimize for that, right? Quantum computing is a bit like that. You already have quantum hardware available within pretty much every cloud provider out there. They offer quantum computing hardware on which you can today go and run real quantum applications, right? But how can you make it more accessible, right? And here again, the analogy I think of is about how CUDA made GPU programming so easy, right? So GPUs have been around for a long period of time, and you typically have things like OpenGL and so on that used to be used for graphics programming on GPU, right? But it's only when CUDA came around that you could use these what were back then specialized hardware for more general purpose computing, right? Similarly, for quantum computing, you're starting to see a lot of quantum kernels that are coming, and you can just invoke those kernels to get something done, right? The kernel could be doing some kind of an optimization solution, could be doing some kind of a machine learning solution. You don't necessarily have to understand the intricacies of how that kernel behaves, but you can just use that as a library, right? So now what we are looking to see is, can you extend something like a functions as a service using quantum functions as one of the functions in your entire applications? Because most quantum applications require both classical and quantum, right? A quantum computer itself is, like I said, like a GPU. A GPU does not do general purpose computing, right? GPU does something really good. It does linear algebra operations really, really well, right? A matrix operation, a tensor operation really, really well, but it cannot be used to run Word or PowerPoint or stuff like that. So for that, you'd still need your classic x86 computing. Quantum is similar to that, right? There are some things it does really, really well. Most things it just cannot do, right? So our goal is to sort of see how you can have a set of classical functions that do the rest of the application. And maybe one of the functions over here could be a quantum function that launches off into a quantum hardware and gets the answer back, and you proceed forward, right? So this again goes towards making quantum more accessible as part of a cloud environment, right? So this is one piece of work that we have going on, and some of this was even done with collaboration with some of the universities like SSN and so on, as part of a summer project, as part of various tangents that came out of this. Another is in terms of how you can use autonomous vehicles or drones as what I think of them as flying computers. I think of them as a flying computer with a sensor on board. And here we are looking to see how we can develop some kind of a drone programming stack. Because today, just like quantum hardware is hard to understand or program, even drone hardware is hard to understand or program, right? So you need to have more specialized skill sets to do that. There's a lot of custom code that you have to write. And here again, we're looking to see if you can make drones again more easily accessible, easily programmable, so that you can go ahead and do very sort of, if you want to do a declarative program, saying that, hey, this drone has to follow that particular individual because they are visually impaired, and you need to give them assistance, right? To give them some directions and so on. Can you do that, right? Or you want a collection of drones to collaboratively, let's say, understand a fire that's going on in a building and give you a three-dimensional representation of that environment so that firefighters could go and try to intervene, right? So we are looking at programmability of drones, of stack for having higher order applications, right? Where you bring in both navigation, coordination, and analytics that the drones can do as part of this programming framework. And one of the key use cases for us is this project called OcuDrone, where we want drones to be able to assist the visually impaired by essentially being a buddy drone that follows the particular VIP, as we call them, visually impaired person, and then gives them situation awareness, gives them sort of prompts in case there's an obstacle in front of them, in case a vehicle is coming towards them, or in case there's a point of interest, maybe a grocery store that they want to go to. They're coming across that, right? That's a use case that we're applying this to. And here again, this brings in a mix of distributed programming, edge computing. We do a lot of analytics using onboard video streams that we get. There's a lot of ML models that we run. Now, do you run these ML inferencing on the edge accelerator that's collocated to the drone? Do you push it off to the cloud? Which are the models that run locally? Which are the models that run remotely? What are the latencies that you require? Maybe if it's something that's used for navigation of the drone itself, you want sub-second latency. You cannot afford to go to the cloud, get a decision in terms of this certain obstacle in front of the drone so that it doesn't crash into it, right? You may not be able to afford going to the cloud. You have to run it locally, right? But maybe there's a point of interest that you're trying to detect as part of a different ML model. That doesn't have to necessarily have a sub-second latency. It could have a few seconds of delay and you're still okay, at which point maybe you push it off to the cloud, right? So how do you even do such scheduling of inferencing tasks across edge and cloud is again a point of interest, right? Again, here again, we don't get into some of the aeronautics or sort of those kinds of control systems kind of algorithm, right? So point being that any computing device, right, can be abstracted away. You don't have to know the fine-grained internal details, but you need to know what its broad capabilities. You can treat it like a gray box or a black box as long as its properties are well known. Then the moment you're able to do that, then you can sort of start putting in all your knowledge in terms of distributed computing or algorithms and scheduling and so on can come into play, and you can start using that. Right? I have a small demo over here. I can sort of show that if it's coming up. No, it's not, but that's fine. So this is just showing a video of how this drone was being able to in real time follow a vehicle, right? A last topic I'll talk about before I start getting into a deep dive around federated learning is again more from a breadth perspective. It's some work we are doing on large-scale graph processing. Here we are looking at how you can look at dynamic graphs that actually change over time. And if you want to perform some kind of a data mining, graph mining or analytics on top of that, how can you do that in real time, right? So here we have some work in terms of processing streaming graphs with temporal features. One example of this could be, let's say you want to detect some patterns that might indicate a fraud in a transaction network, right? So if you're doing some credit card transactions, all the credit card transactions, if you're going from one account to another, they all form one big transaction graph, right? Where the account numbers are the vertices and the edges are the transactions between them, right? If you got such a large transaction graph, when a new transaction comes in, can you mine for patterns? Do you see some patterns that might indicate a fraud or some kind of a misuse of that card, right? And in real time, you can sort of decide how you whether you decline it or not. So this status is a framework, so it's a distributed framework to enable doing that in real time. So we also have some work going on in terms of federated learning over graph neural networks. Graph neural networks combine both machine learning neural network models as well as graph topologies. The graph neighborhoods itself is captured as embeddings within this neural network, so that you can make use of not just the features on the vertices or edges, but you can make use of the features present on the neighborhood of a vertex or edge in order to do such training. Here again, we have work going on in, some of it is in federated learning, which I'll talk about, but we also have work going on in terms of inferencing over such neural network graphs, again at large scale, right? So all this is to show that each of these things might seem very different, but at the end of the day, fundamentally, all of these are distributed systems. It's about how can you make use of distributed computing systems in order to support various applications, right? And we take a very broad view of that, right? Again, everything I'm going to talk about, I've been talking about as part of a bunch of very smart students and dedicated students that we have over here, and staff and some of our collaborators such as Sajal Das, who's over here. So like credit due to them for everything. And with this, I'll actually move on to the specific focus of today's talk, which is on federated learning. But before that, Chika, just want to check, should we do Q&A at the very end, or would you like to do it in between? How has the protocol been?
It's up to you, sir. No problem. If you prefer that, we can open quickly.
Okay. After every sort of major section, maybe I'll take a pause. If there's any question, I'll be happy to take it right now. And if not, I can take it after the next section has been covered. Any questions so far? Just checking to see if anything in some chat window as well. Okay, so let's move on. There'll be multiple chances to ask questions. So talking of federated learning, let's talk about where the need for federated learning comes from, right? So as we all know, machine learning has really sort of taken off in the last decade or so. And that's partly sort of a mix of a large corpus of data being available, as well as the advancements that have happened within research going on with it, neural networks, deep learning, and more recently transformer models and so on, right? Pretty much every website or every app that you use is collecting data about you. Even as we speak, Google is collecting data about all of us as we're using Google Meet for this call. So there's a large corpus of data that's out there, right? And that's really one of the reasons why ML has become successful. And data being one side and the models themselves being the other side of the coin, you have these massive advancements in these transformer models, especially in the context of generative AI and so on. And if we thought machine learning was very compute intensive and you need GPUs for that in the past, just with DNNs and CNNs, with transformers, you need tens or hundreds of GPUs in order to be able to train these models, right? And these foundational models, as they're called, are large enough that only probably a dozen entities in the whole world can afford to train them, right? Training each foundational model from scratch costs $1 billion, right? That's the size of a small country that we're talking about, right? The GDP of a small country. So this is costly, compute intensive, and so on, right? So, and this is also starting, it's a bit of an arms race, right? So this is from a few months back, right? This is probably earlier in the year, right? But even now, I'm sure this data is already out of date, right? I'm sure everything has gone up by 20%, 30%, or 50% in terms of the number of parameters that are out there, right? And the cost of training such models, right? So what it means is that there's advances both in the data side as well as the ML side that are making it possible to do very interesting things, right? And a third piece of the puzzle that comes up, right, is, again, this sort of relates to the data source, is this notion of Internet of Things, right? And Internet of Things talks about having sort of a lot of sensors, a lot of physical sensors that are observing your physical environment, and you're able to sort of collect a lot of streaming time series data from these various sensors and accumulate them for taking decisions, right? These span everything from some smart cities where you might have, let's say, traffic cameras that might be present in the city. You could have metering that's going on within your metros, ticketing stalls, and so on. You could also have power grids, right? So your electric grid could have a smart meter in your household. All these are examples of IoT deployments that are present within smart cities, right? And top of that, we start looking at things like industrial IoT, where factories and manufacturing units have a lot of sensors to monitor their equipment to see if they are working fine, right? You have medical devices, right, that are internet connected, right? So where many of the fMRIs and many of the medical instruments, if you go to a hospital, are actually connected to the internet. Meaning they might take a image, they send it off to the cloud, it does some processing, and it gives back some kind of an analysis of the medical image, right? These things are getting much more and more common. But IoT is essentially a mix of affordable sensing. Sensors are getting cheap. Communication is everywhere. You take it for granted that you have 4G or 5G connection or broadband connection everywhere. And you have the ML models that come together, right? All three come together in order to solve what are called these closed loop cycle, where you observe, you orient based on the observation, you use things like analytics and ML models to make certain decisions, and then you actuate. You actually take an action based on that to improve the system, right? So for example, you might see that you might use a sort of traffic camera to see that the traffic flow, you're capturing a series of images of, let's say, a particular traffic lane or a traffic junction. You sort of use an ML model, a vision model to extract, let's say, the counts of the various traffic flows in these various intersections. You look at sort of a different model, maybe some kind of an optimization model that tells you, hey, given this current traffic condition, what should be the signaling pattern? And based on that, you might send a signal to your traffic signal saying that, hey, change it from red to green, or change the cycle from, let's say, a 1 minute, 60-second cycle to maybe a 90-second cycle, right? So that's an example of, and you then go back to observing. You observe if changing it from, let's say, 60 to 90 seconds for a traffic signaling pattern helps improve, or it helps reduce the congestion or improve the traffic flow, right? And if so, you're good. If not, you again maybe do this whole loop again and make some corrections and so on in a closed loop cycle, right? So IoT applications typically have this model, right? So observe, orient, decide, act, and you keep repeating it, right? And this is where, again, there are multiple such examples of this IoT deployments within smart cities. There's work that we've done with air quality monitoring, where we had these IoT deployments. You had all these sensors, low-cost sensors that were observing the parts per billion of various gases like ozone and sulfur dioxide, and particulate matters like PM10, PM2.5, and so on. We had edge devices such as Raspberry Pi, which sort of collect that and push it to the cloud and do various visualizations and decision making and so on, right? But that was a case where you pushed all the data, right? This is about 5 years back, where this cloud was still the best bet for dealing with data, right? The edge devices were mostly used for collecting data and centralizing it to the cloud, right? So typically IoT data, right? And these edge devices would be Raspberry Pis or even embedded devices that would be there, right? But nowadays you're starting to see these edge devices start getting more powerful, right? So recent work that we did in the power grid domain, right, was in terms of understanding how we can do power demand predictions. Let's say you have an edge device that's on site within a particular, so let's say there's a software park, right, a software technology park, and you have power metering, like electricity metering that's happening in every building, right? Now the question is, can I predict what's going to be the power usage for each of these consumers, right? Using some kind of a prediction model, some kind of a DNN model, right? But here you get into a little bit of a tricky situation, right? Because the power usage by a company can actually be sensitive data, right? Let's say you have an IT company that's suddenly starting to use more electricity in the middle of the night, right? That might actually indicate that maybe they have a big product launch that's coming, right? And this might mean, because you have people working 24/7 shifts, and this might mean that your competitor might get a advantage, right, by knowing this information, right? So electricity usage information itself can be very privacy sensitive information, right? So now the question is, if the consumer says that, hey, I will not share my real-time power usage data with you, maybe I'll only give it to you once a month, right? Once a month, I'll tell you how much electricity I've used, and you can bill me for that, right? But if you want to do, let's say, predictions for deciding how much power to purchase, right? Because the software parks and maybe large even cities and so on, they actually have to plan for their electricity supply for the next day or several days upfront, right? Because electricity itself is not like a constant commodity. Every day there is actually, they go to the spot market, they purchase as a base load, supply the base generation that is there, maybe from your static sort of coal-fired plants or gas plants and so on. There's a dynamic factor that comes in from solar and wind, because these are intermittent, these don't give you steady supply. And then the demand itself can vary across time, right? In such a dynamic environment, right? So if there's a mismatch between your demand and supply, you actually have to go to a spot market, an electricity spot market, and purchase power for the next day, right? So this is where demand prediction becomes very important, right? And even at the single technology park, demand prediction becomes important, right? So here, this is a great example of why federated learning would be useful, right? If the consumer says, I won't give you my raw data, right, but I'll allow you to run some kind of a training model on my raw data, right? You send a model to me, I'll run the model, I'll give you a trained model, but I'm not willing to give you the raw data, right? So here is where something like federated learning comes in, where you want to keep the data private, right? The training data itself that's being generated from these various clients are kept private with that particular entity, but you want to train a machine DNN model, let's say, right, on top of all this data, right, without centrally collecting this data. What do you do, right? And that's where federated learning comes into play, right? So we'll talk a lot more about that, but this is a motivating use case for why you might need privacy preserving machine learning, right? So this is just to give you an earlier example. In fact, some of this FL work is even happening in the context of sort of Bangalore city. This is an example of, this is a new project that we are starting. We have a Center of Excellence on Urban Mobility that's coming up. This is one of the junctions in Bangalore, in Indranagar. And here, we're just running a sort of retrained YOLO model over here. Nothing fancy here. You must have seen such videos many times. But the interesting bits over here is that we have retrained the model to make it more accurate for Indian conditions. And you see these white lines over here, that's effectively doing a vehicle counting. It says that, hey, a lane ends over here, another lane begins over here. So whenever this box crosses this lane, we know that that's the count of vehicles that are going that particular direction, right? So that's something that's happening. So what this shows you is that you can go from the visual spectrum to something like a time series spectrum, right? And with the time series spectrum, you can overlay it on the network of the roads, and you get into a temporal graph spectrum, right? So all these things are layered on top of each other. And here again, if I want to do some kind of a inferencing, right, or a training, I don't want to always pull data, right? Bangalore has 6,000 traffic cameras, and they spend a lot of money in terms of paying for bandwidth, right, to pull data from all these 6,000 cameras into their private data center, right, that's sitting in their traffic police office, right? And they pay for a lot of money to store this data, let's say for a month at a time, right? So they have about several petabytes of storage that they have, right? Now, if you say that, hey, I only want to, I don't want all the data to be archived all the time, but I still want to be able to train or infer based on this, right? You can always keep a little bit of data cached at the edge, because co-located with these cameras, you could have, let's say, an edge device like a Raspberry Pi or an NVIDIA Jetson, right? And I can push my training model or my inferencing model to these edge devices and then do the local training or local inferencing and only give me the output back, because the output is going to be much smaller in size compared to the raw video data that's coming out, right? So another reason to do federated learning is to avoid the bandwidth for data transfer between the edge and the cloud, right? So the two key reasons: one is for privacy, where you don't want to share the data from the edge to the cloud. Another is for performance, where you don't want to move a lot of data and consume bandwidth to go from the edge to the cloud in order to do the training, right? So that's one part. And the other part to add to the hardware mix is that you have all these hybrid cloud environments, different cloud providers. So there's one flavor of federated learning where this again is motivated more from the privacy side of things, right? Where you might have different institutions, different organizations, right? Let's say you have different banks that want to train a fraud model, right? They want to understand, or they want to do a credit risk score, right? So, credit scores are very popular nowadays in India. So if you want to go for a loan, they'll immediately ask, they'll calculate they'll go to an agency to get a credit score, right? But let's say banks want to get together and they want to train a common model for doing credit scoring, right? Based on the account information and so on, right? But obviously banks cannot share fine-grained account transaction details for all their customers with any central entity, right? Unless it's RBI or something, right? So how do they train a common model, right? Here again is a question of privacy, right? I want to keep my customer data local. And similarly, every bank wants to keep their customer data local, maybe in their own respective cloud data centers. But I want to train a common risk model that all the banks can share, right? Here again is a great motivation for federated learning, where the local model gets trained in each of these local data. It gets aggregated, it gets pushed to a central entity where it gets aggregated, and then you do that, right? This is again, we'll talk a lot more in detail about this, but another motivation for federated learning, right? Talking about the edge themselves, these are various flavors of edge devices that are out there, and they're starting to become more popular. So these are several of these are NVIDIA devices, but you also have especially things like the AI PCs and so on that are starting to come on board to support Gen AI bots on your laptops and desktops. They're also starting to be a accelerator, an edge accelerator might be present on every computing device in the near future, right? So give me a second, I'm going to turn off my Teams because that's interrupting a lot. Let me disable that. I don't want the distraction. Okay, great. So final exam grades are due this weekend, so students are really anxious about what scores they got. That's why there's a lot of pop-up messages that we are seeing. So we have all these edge devices, edge accelerators that are present, right? And these are very small in size, right? So this is literally the size of it's an external hard disk, right? It's the size of a palm. I mean, each of these devices could easily fit in my hand, right? So these are very compact devices, right? And these are the ones that are being deployed on things like, can be deployed as part of smart city. You know, this could be co-located with a traffic camera. This could be co-located with air quality monitor and so on, right? So now we got hundreds of such devices out on the field, right? How can you put them to use, right? And this is where the notion of a computing continuum comes into play, right? You have all these sensors, you got these edge devices that are typically going to be connected to your sensors, right? Sitting right next to them, right? And you have your backend cloud that's there. And in between, you could also have something called a fog, which is a bigger accelerator, maybe a couple of workstations and so on that are sitting there. With 5G coming around, you might have more computing power present along with your cell phone tower that you can tap into. That's an example of a fog. But bottom line is that this is a spectrum, right? So starting from the edge sensor all the way to your cloud data center, there are layers of these computing hardware that are present, right? So now, can you make use of all of these things together intelligently? Right? That's a bigger question, right? That's worth examining. And one part of a big question is, how can you use it specifically for doing distributed machine learning? And that's where the federated learning comes into play, right? All right. So with that, well, maybe I should have skipped it. One way to think about this problem in its entirety, right? So just about federated learning, the bigger question to ask ourselves, right, is if you have all these heterogeneous edge, cloud, fog, accelerators, kind of computing hardware that's available, right? How can you put them to the best use, right? What are the algorithms and software platforms and strategies that you have to use in order to perform machine learning training as well as inferencing on top of that, right? Because ML is a very important workload. So if we take the big stack diagram back there in the original pyramid that you saw, the top of the pyramid right now is going to be machine learning. The bottom of the pyramid is going to be your edge, accelerated edge and cloud hardware. And in the middle sits in the platforms that are necessary to efficiently train and infer ML models on top of such distributed and accelerated hardware, right? All right, and with that, we'll go dive into federated learning itself. But as before, I'm happy to take any questions if you have in terms of the context that we set up for federated learning. Any questions or comments? Okay, so let's move on, right?
Hello, sir.
Yeah, go on ahead, please.
Is the federated learning only used for privacy preservation or providing the security to the network or in the cloud or edge devices? Or this is the only purpose of the federated learning, or any other machine learning technique is available to secure our network?
Right. So federated learning does not have to do with security of the network at all, right? So federated learning it's important for privacy of the data that's present on the edge. And the privacy of the data might be even more important if your network itself is not secure. Let's say the link between your edge and the cloud is not a secure link. You don't trust that communication link, right? In which case, though you're willing to share the data with the cloud, you may trust the cloud, but if you don't trust the network link, then you will not share the data, right? So there again, it comes down to security and privacy being the reason for doing federated learning. But using federated learning for security is a different problem, right? At that point in time, there are, for example, research that goes on into training, let's say, malware detection models, right? So here you can use federated learning, right? But the model that you're training exactly becomes, let's say, malware detection, right? So this is a use case for federated learning. But federated learning itself, the primary reason is for privacy of the data. And another secondary reason is to reduce the amount of data that you're transferring because the data is very large, right? And you're going to spend a lot of resources moving data. Okay. All right. I see a raised hand.
When we train our model on the local devices,
Yes.
on the IoT devices, edge devices, so the privacy or the data is we are getting average of the model to the final on the model. So how we can conclude that the model is trained on the actual data means we are getting the average of the model from the IoT device to the central node. So how we can assure that the actual training is happening or not?
Right. So I would suggest let's hold the questions on the internals of federated learning till after the next take off slide. We'll get into details of how federated learning happens in the next few slides. But so far, we are trying to set up the motivation for doing federated
learning. Sir, very good evening, sir.
Yes, please.
Sir, myself, Dr. Palani from... Hello, sir. Is it audible, sir?
Yes, it is, please.
Yes, sir. Sir, myself, Palani, Dr. Palani from professor from Hyderabad, sir. Sir, I have queries from related for how implement for IoT devices embedded with firewall concept, sir. Generally, firewall it is implemented for it is a static rules. How it is implemented for the dynamic rules, sir? So for example, if your IoT devices were installed for home or any door or any other our home like any other devices, how to implement for the firewall concept, sir? Any other ideas or suggestions, sir?
I'm not an expert on security. I'm not an expert on firewalls. So I cannot hazard an answer on that.
No,
So,
because it is related for edge devices. No, that's why we have to asking any idea. If we have any tools is there, we have to predict it for the any prediction is happen for related for devices, sir.
right. So I'm not an expert on the networking layer of the security layer for edge devices. Just like I'm not an expert on architecture, right? So
Okay,
there
sir.
are
Fine, sir.
100
Thank you,
different
sir.
problems that you can solve on the edge. My knowledge is more limited to what I work on, right?
Okay,
That being
okay, sir.
said,
Fine, sir. Thank you, sir.
what
Thank
you can do, the federated learning itself, like I was telling to the earlier speaker, it can be used to even learn such firewall rules, right? So for example, if there are ways, strategies, again, there's a lot of literature that's there on that. I'm not fully familiar with that. Some of my colleagues work on that. But you could use federated learning to learn how such security rules could be imposed under what conditions, right? And a way of training that, because again, many of the network logs that are going to be collected can be very large in size, or they might be sensitive in nature, right? So within network security, I know there's a lot of interest in applying federated learning in order to learn such rules, right?
Hello, sir. Good evening.
Yes, please. So if you don't mind, just raise your hand so that we can go in sequential order.
Yes.
Yeah, go on ahead, Lakshmi. Yeah.
Sorry, sir. So there are private clouds and public clouds. So this this edge computing, where does this fit in actually?
Okay.
And I missed the slide. And
Sure.
also, will this edge computing will it be replacing the cloud computing, whatever we are using right now, the Oracle cloud or any other cloud, Microsoft Azure clouds we are using right now? So will it be replacing it any in real time sooner than what we expect to be?
Sure. Great question, right? And sorry for skipping over that particular detail of this slide, right? So the way to think about, okay, let's take a step back, right? So if you look at, first of all, there are various cloud providers, like I said, AWS, Google, and Azure are probably the three big ones, globally speaking, right? And each cloud provider has their own cloud fabric, cloud software stack, and so on. And each cloud provider has many, many data centers, right? So within India, they have maybe 3 or 4 data centers each. In the US, they might have dozens. In Europe, they have it, Singapore, and so on, right? So cloud providers have many, many data centers, right? So what edge computing does, right, is it complements this, right? Edge computing could be anything from a smartphone itself as an edge device, right, to you could have a device that's, let's say, sitting within IISc, right? As for the entire IISc, there's one maybe a high-end server or a cluster of workstations or GPU servers that might serve as an edge within IISc, so that maybe some workloads from IISc might be executed on this cluster. Some might be actually pushed to a public cloud, right? Or these edge devices could be part of, let's say, a 5G base station, right? Maybe Reliance Jio or ATAL, or even, for example, more traditional content distribution networks like Akamai. They might actually say that, hey, I will provide compute. I'll provide compute for you within your city area network, right? Within Bangalore, I'll have, let's say, 20 of these fog or edge devices, right? Which each of them might have a few servers or so on. And that way, you don't have to move data between the cloud and your consumer. One great example is Netflix or Amazon Prime, right? So all of us watch movies online, but you can be fairly sure that the movie you're watching is not coming from some data center that's sitting thousands of miles away or thousands of kilometers away. It's most likely, if you're in a major city, it's coming from a local CDN in that particular city, right? So that's an example of edge storage, right? Content distribution networks are examples of edge storage. Now, these are getting upgraded to edge computing, right? It's not just data that you can access from these, but you can actually run computing on top of that as well, right? So edge computing itself comes in many, many different forms. And so in that sense, it's much more heterogeneous compared to just a cloud, which traditionally is seen as just a data center managed by a major service provider, right? Can you remind? So the second question is: edge going to replace the cloud? Absolutely not, right? So edge devices, I mean, clouds have become extremely popular in the last 20 years for a good reason, right? The reason being that it's very hard to manage large-scale computing hardware, right, in your own premises, right? So I partly help managing the data center in our department, and it's a lot of work, right? You have to take care of the cooling, the power supply, the safety, and so on. And even if you sort of outsource it to a vendor, it's still like at least once or twice a month we need to go check and so on. So most enterprises don't want to do that. They don't want to spend the effort and time, and they don't have the expertise to manage local data centers within their companies, right? So public clouds are a great way to outsource that, right? Given that network speeds are extremely high nowadays, broadband is taken for granted. You can keep all your data and the computing resources, you can lease it from public clouds, and you yourself can just have the clients that are there, your laptops and your desktops could be, or your smartphones could be accessing this data. And the computing and your applications and your data are going to be residing on the public clouds, right? So this benefit still remains, and you also get cost efficiencies, right? Buying the cost of buying a single server is going to be much higher per capita than the cost of buying 1,000 servers, right? If you get 1,000 servers, you'll probably get a 30% discount, right? And if you buy a single server and keep it in your lab or your department, I can bet you that the utilization is not going to be more than 25% or 10%, right? Which means 90% of the time or 70% of the time, the hardware is idle, right? So cloud providers have solved this problem, right? They get large hardware in bulk at cheap prices, and since they have a lot of consumers, they're able to shape the load so that the utilization is extremely high. It's very efficient, right? So the costing and the management benefits of public clouds are too beneficial for anyone to move away from the public clouds. That being said, edge devices or edge computing is useful in several niche areas, right? Like I said, content distribution for movies, right? Or doing edge analytics because you want very low latency if you want to do traffic signaling, right? Or the data itself is being generated on the edge and you don't want to keep it pushing to the cloud, either because of large bandwidth consumption or because of privacy reasons, right? So there are certain cases, maybe 10% of the cases where edge computing is relevant, but for the remaining 90% of the case, cloud computing is still the preferred model. Okay, hope that helps.
Thank you, sir.
Sure.
Good evening, sir.
Good evening.
Sir, can you please describe is federated learning algorithms are running on edge servers? Is that so, sir?
Yes, they are, and we'll talk a lot more about that in the upcoming slides. So
Okay.
federated learning will run both on the edge and part of it on the cloud, and we'll discuss that in more detail. Yeah.
Sure, sir.
Hello,
Thank
sir.
you.
Dinesh, go on ahead. Yeah.
Yes, sir. You have tell about the quantum computers is relating with the this edge devices and edge computing. So because quantum computing is different area and cloud computing is totally different area. So I am not able to understand how their integration is happening and how the research is happening in these areas.
Yeah, I was in your same camp. That's why I said if you asked me 3 years back, will you be working on quantum? I would have said the answer is no, right? But here's where they are related, right? So let me see if I can pull this slide. So if you take a cloud data center, right? So quantum computers are costly, very costly, and quantum computers are they are strategic assets, right? Countries will not let you export a quantum computer, right? Because these are strategic. Nowadays, you're seeing even GPUs, the US is not even allowing GPUs to be exported, high-end GPUs to be exported to China, right? And quantum hardware is even more sensitive, right? Which means that unless they are your best friends country, you cannot. I think the only quantum computer that's been, for example, that IBM has been allowed to ship outside the US, I think one of them is in Japan and the other is one in Germany, right? So given that these are strategic assets and these are very costly, and they need a lot of very sensitive environment, right? It's not just like you need for a server, you just need a cold room with UPS supply and you're done, right? It is not terribly difficult to achieve. Quantum computing is much, much more sensitive, right? Hence, the most practical way in which you can access the quantum computer is within specialized locations, right? And since you already have data centers all around the world, it makes sense to actually co-locate a quantum hardware alongside your traditional data center, right? That's one thing, right? The second thing, a quantum computer by itself is useless, right? You can probably do one thing, right? Or a few things really, really well. Everything else, you need the use of additional traditional computers, your traditional servers have to do that, right? For example, you might just do one optimization piece of a large application, right? It might be a very time-consuming part of the application, but just doing that particular piece is not good enough. You need to have the entire application, right? So which means quantum computing requires traditional computing also, right? That's all the more reason to co-locate quantum hardware with your traditional data centers so that the classical part of your application can run on your traditional x86 servers, and only the quantum part of your application will be executed on the quantum computer, right? So the way I like to think about it is, and that's sort of the light bulb moment for me, quantum computer is like a GPU, right? A GPU by itself is a useless piece of hardware, right? It has to be part of an overall system, right? For me to use the GPU. Same thing with a quantum computer. I need to have a quantum computer sitting alongside a regular server for them to jointly perform an operation. Okay.
Okay, sir.
Hopefully that helps. Yeah. Any other questions? Okay. If not, let's move on to how federated learning works, right? So far we're just setting the motivation and the context for federated learning. Let's actually talk about federated learning, right? So this is the big picture, right, of the interactions between various entities of federated learning, right? So you have a set of edge devices or client devices or client machines, I should say, because federated learning can also happen between servers, right? But here, a set of computers or edge devices that have access to local data, right? Each of these devices have some local data, D1, D2, D3, so on to Dn, right? Which either for privacy reasons or for bandwidth reasons, they are not willing to share with any central entity, right? Let's say this is a central entity, which could be sitting in the cloud, it could be a private server. It's essentially at some, it's either in a different security zone or in a far off distance, network distance, compared to these edge devices, right? Now these edge devices are not willing to share their data with a central entity, but all of them want to use their collective data to train a machine learning model, let's say a DNN model, right? That's the context, right? Now what happens, right? So the assumption, one of the assumptions that we're making over here is that the trained model itself is not privacy sensitive, right? The model itself will not reveal any private information about the clients or the private data, right? That's the assumption, and it's reasonably good assumption. Of course, there are counterpoints to that have been shown, but for the most part, that is the case, right? So what happens is that you take the model architecture. Let's say your standard DNN training starts off with the model architecture, and all the weights that you want to learn have been initialized to some random weights, right? You start off with the model architecture with some random weights. That's what we call the global model version 0, G0. Now you take this global model, version 0 of the global model, and send it to all the clients, right? In the simplest case, you're sending the same model to all the clients. You send G0 to each of these n clients. Each client takes the global model, and then it starts a local training, a local DNN training using this model architecture. And it starts with these random weights, does multiple epochs of iterative training, right, on top of this local data. And at the end of it, right, you do multiple epochs of training. One epoch will do a full scan through your training data in mini batch, right? And you do multiple epochs, which means that you keep training multiple times over the same data until you get a locally trained model. This L1 that you see started off with G0 as the starting point, and the L1 model has been trained on D1. This happens on every edge device, right? So this device N, it would have taken G0 and trained it over Dn data and gives you the local model Ln, right? Now you have N local models, right? Each trained on a different private data. These clients send their local models to the central server. Right? L1 through Ln gets sent to the central server. The central server aggregates, takes this L1 to L1, performs an aggregation step, and gives you a new version of the global model, G1. Right? So now G1 has the characteristics of all these local models, right? So, and G1 will tend towards, it will have its model features or its model parameters will start having the flavor of the model features of all these local models. They're still not done, right? You just got G1. What do? You take G1, you send G1 to all the devices. And then they'll start with G1, and with G1, they'll again train on the local data to get the next version of their local model, right? This again, they'll send it back to the central server, which will again aggregate it and get version G2. Now, each time you do this, it's called one round of training, right? So one round of training is this central server sending a global model, the same global model to all the clients training a local model, starting from this global model, using their local data, the clients pushing their local models back to the central server, and the central server aggregating all these models to get a new version of the global model. This is one round of training. And typically you do many rounds of training, sometimes even hundreds of rounds of training, until the accuracy of your global model starts approaching the accuracy of having trained over a union of all the data. Right? The classical way of doing this is you send D1, D2, D3, Dn all to a central server. And in the central server, you do multiple epochs of training. So doing that, you're doing it by model aggregation. So model aggregation takes longer to converge compared to just data aggregation, right? And sometimes model aggregation may never, federated learning may never get you the same degree of accuracy or same global model as using a centralized data, right? But that's sort of some of the trade-offs that you end up doing, right? But at the high level, that's pretty much all federated learning is, right? It's the concept is very, very simple, but there are lots of nuances to that as we will talk about, okay? All right, so again, we talk about the use cases. If the data is large, you don't want to send it. If the data is sensitive, you don't want to send it. Medical data, fintech data are examples of sensitive data, and video data is an example of large data, right? Now, there are many flavors of federated learning, right? So what we said is sort of what's called a federated averaging. Fed average is the default federated learning that I talked to you about, right? So the two key things that FL plays around with is how you do the aggregation and how you do the client selection. Okay? Because in this example that I mentioned, I said that all clients will get the global model and all clients will train a local model and send it to the central server. That's actually not true all the time. So this is an example of what's called a federated averaging, right? And in federated averaging, you choose all the clients in every round, and the model, that the aggregation that you perform on the local models is just a simple weighted average of all the layer weights. So for every layer, let's say you got a 5-layer neural network, each of these L1 through L1 will have 5 layers of your parameters. And all that you do over here is that take each layer across all the N models, do a weighted average, and you weigh it by the size of the data. If this has 10 data items and this has 20 data items, this will get 10% weightage and this will get twice the weightage of this one. You just do a layer-wise average. That becomes your global model. So this weighted average being the aggregation and all clients being selected as your client selection is your default fed average federated learning model, right? But these are two things that you can play around with, and as you play around with it, you get different FL strategies, right? And that's what federated learning frameworks try to support, right? So there are frameworks. There are some frameworks out there that will help you train FL models, right? The original paper that made FL really popular came from Google, and Google was trying to do FL using their Android phones, right? Because Google, being like any major web company or internet company, Google is always in the crosshairs when it comes to privacy because they hold a lot of private data. So they try to reduce the risk by coming up with strategies where they can avoid collecting private data, right? So Google started adopting federated learning to help them. The simple use case that they give is that Google keyboard, the Gboard keyboard that you might have in your Android phone. It gives you predictions. If you start typing, right, in your smartphone, you'll start the moment you start typing in 1 or 2 characters, you'll start getting a prediction saying that is this the word that you want to use. The moment you select that word, it will give you 2-3 more words saying that here's how you want to this is how you want to complete your sentence. How does it predict these things, right? It predicts it because there is a small machine learning model that's running in your keyboard on your smartphone that looks at your prior words in your sentence, and using that, it predicts the next word, or it predicts the completion of the current word, right? So these are machine learning models that are running on your smartphone. But who trained these models, right? To train this model, Google would have seen, or the Google keyboard would have seen, the way in which people complete a sentence for millions of users across the world, right? So things that you're typing in your Google keyboard or your Swift keyboard or your Samsung keyboard and so on, all these are actually being sent to these respective companies to help them train these auto-completion training models, right? Now, what Google wants to do is say that, hey, I don't want to get the data that people type in the Google keyboard to a central server. That's too much privacy risk for me. If I accidentally reveal it, I'll be in a lot of trouble. But I still want to keep training my model. I want to improve my Google keyboard model so that my predictions become more accurate. How do I do that? Federated learning enters the picture. You might have a very basic next word prediction model that you've trained, maybe from public sources. Now you send these models to all your Android phones. Locally, the keyboard would have collected local completion data. Locally, the keyboard would still be collecting what are the next words that the user is typing, right? Now, using this local data that's been collected on all these keyboards, you start with a global model, you train it on your local data, and come up with an upgraded local model, right? Now, this local next word prediction model is pushed to the Google server from all your Android phones. Google aggregates all these models to get a better global model, right? Now, this new global model would have updated knowledge of the completion by all the different Android phones. Then it pushes it back again and repeats it until you have a much better model. And now, once you have this, what you do? You'll put it as part of your next version of your keyboard. Next time you go and do an update of your Google keyboard, it'll get a new prediction model, which will hopefully be better than the previous version of the keyboard. Okay, that's sort of the brainwave, or that's sort of the canonical application which made federated learning really popular, right? If people realize that, hey, if Google can do it, I can also do it, right? That's what made things popular. Right? But the catch is that, I mean, Google, while the idea itself, Google shared this idea, they said it works and all those things, they didn't make the code itself available, right? So you started having a lot of these open source federated learning frameworks that would help you set up an FL environment. It will help you set up your clients. It will help you set up your server. It will help you orchestrate these entire interactions. All these interactions that we see, someone has to coordinate all these things, right? The local model training itself is very simple. You can use PyTorch or TensorFlow to do the local model training. That's the easy part. The more difficult part is all these interactions that take place between the clients and the servers and the aggregation that happens, right? So these have to be carefully coordinated, right? That's where you start getting FL or federated learning frameworks, right? But these again have their own set of limitations, right? So the popular ones out there, Flower from University of Cambridge or Cambridge University, is one of the most popular frameworks out there. It's very lightweight and very reasonably easy to use, right? There's also USC has FedML AI. Intel has an open source project with, I think, University of Michigan on OpenFL. You have PySift by one of the Chinese banks. You got Leaf from an open source community and so on. And TFF, TensorFlow Federated from Google, that itself is, it's not quite a federated learning framework. It's a simulation environment, but not a FL framework, right? And all these other ones have several deficiencies, right? And we'll talk about that in a minute. But what we did is, in the last year and a half, we saw that none of these were meeting many of the requirements that we see as being important. And we developed our own FL framework called Flotilla, right? Which I'll use as an example to walk through some additional details on FL. But one of the key requirements is for an FL framework or an FL strategy is to select the correct set of clients on which you want to train a FL round, right? Why is it important? In the case of Google, they might have 2 billion Android phones, right? Trying to train a model on 2 billion Android phones in every round is very, very difficult, right? Devices will fail, devices might not have enough resources, you might run out of battery, and you might get a lot of models. A billion models might not be very useful, right? So instead, you want to be smart about which clients you want to train the model on, right? And if you think about it, what are the best clients that you want to select? Best clients are those that have very diverse data, right? If two clients have almost the same data distribution, right? Again, not the same data item, the same data distribution, right? So it might not be very useful, right? So me and my colleague at IISc might have very similar data in our Google keyboards, right? So getting local models trained on both our smartphones may not be very useful, right? So you want to have a selection of clients such that they have different flavors of data. And when you get the models from all of them, local models from all of them, you aggregate it, that will be more representative of a global model, right? And much lesser amount of work that you have to do compared to having all the billion phones to train a model. So client selection becomes important. How can you incorporate very interesting and innovative client selection models is a key requirement, right? Another one is in terms of custom aggregation as well, right? So the other part of it is that if I get all my local models, how do I combine them together, right? Simple averaging or weighted averaging is one way to do it. But there are also other sophisticated strategies. They might say that, hey, this particular client had data whose distribution I've not seen before, right? So this time, in this round, I'll give it more weightage, right? It might not have a lot of data, but it's rare data. Since the data is rare, the model that it returns to me will be given more weightage. That's one example of how you might do it, right? Or you might say that depending on how many times a particular client has been used in the past, if the same client has been training more repeatedly, I'll give it lesser weightage so that I don't get biased towards that particular client, right? So there are many such strategies that exist for doing model aggregation, right? So here again, we need to have ways to be able to configure such selection strategies, right? And lastly, there's this notion of asynchronous averaging. The examples I told you before are what's called synchronous averaging, right? What that means is that once I select a set of clients for training the local models, my server will wait until all of them return a local model, and then I'll do my averaging and start the next round. But let's say one of these clients is very slow, right? And it's taking forever to complete its local training. Everyone else is waiting for that client to complete. So this is one of the downsides of synchronous averaging. So asynchronous averaging says that I will, as and when I get a local model update, right? As and when I get maybe a few local model updates, I'll immediately create a new global model. Even though others are still doing their training, I'll create a new global model and send it to the clients that gave me a local model, right? So which means that this particular client might be having a newer version of the global model and keep doing a round of training, while some clients might be having an older version of the global model and doing their training, right? But as and when I get updates from the local clients, I might incrementally keep doing a aggregation, right? Here again, there are many, many different strategies in terms of how you do it so that you balance between accuracy of the model as well as the skewness that might come up. If there are many fast clients that keep training very, very quickly, the model might get biased towards their data, right? So asynchronous averaging itself is very interesting research problem, but not, in fact, none of the other frameworks support asynchronous averaging. The FL research itself has gone much ahead, but the frameworks to support such research is still lagging behind, right? And frameworks are important because you don't want to write code from scratch every time you have a new FL strategy. If you have a new FL strategy, you don't have to go and start from the first principles and be writing code. Frameworks are useful to quickly try out various strategies, right? Of course, the kind of framework for doing the ML training itself, local model training itself, could be both PyTorch or TensorFlow, the two popular ones. Again, many of them support, most of them support TensorFlow, but PyTorch does not support with everyone. Dealing with client failures is another important thing. Let's say you launched FL training round. We had 2 clients failed, right? Now what do? You wait for them to be rebooted and come back again? You sort of cancel the entire round and start a fresh round, right? You take the partial results and continue on, right? So those are things that the framework has to give you hooks, give you capabilities of handling client failures, right? Server failures is also important. It's rare, but it's still important, right? Let's say the server fails in between, right? Then you lose all the trained global models that you've been doing so far. Because like I said, FL training can take several hundred rounds. Sometimes it may take days together to complete your training, right? Let's say you're almost close to convergence and you lose your server that does the aggregation, you lost things, right? So there again, server reliability is something to support, right? And then there's a bunch of things that go towards the deployment side of things, right? Because at the end of the day, many of the FL frameworks out there are more for just some very quick and dirty testing, right? It's more to check if your FL strategy works rather than for actually deploying it in an operational environment. Of course, people like Google have their own operational frameworks, which is private, which is proprietary to them. They don't make it public, open source. So here again, you need to be able to deploy the model architecture on the fly. You should be able to run it within containers so that it doesn't affect the other applications that might be running on the device, or it doesn't accidentally leak data. You need to be able to have new clients join the cohort and clients leave, because clients themselves might not be constant across time, right? You need to be able to deliver the model and its dependencies to the client. So a bunch of things that have to happen on the operational side to even set up an FL environment and start training. Right? That again is capability that many of the existing frameworks don't give. Right? So that's one of the reasons why we went ahead and said, hey, let's build a framework that actually does a good job of all these things. Wherever possible, we'll reuse ideas that already exist, right? And if it doesn't exist, we will fix it and bring in our own contribution. So that's the big picture around Flotilla, right? But before I get into internals of Flotilla, I'm happy to take questions on FL, federated learning itself, as a concept and how FL itself happens. Right? Let me pause and take questions. I see a raised hand from Lakshmi Rupa. Please go on ahead.
Yes, sir. So in a broad way, when we talk about machine learning techniques, there are so many like supervised, unsupervised learning techniques. So where would this federated learning fall in? And the second, my second question will be, we already have so many techniques going on. So how would this federated learning edge over everything else, or where is the scope for even more for this? So there might be some limitations and there might be some advantages of this particular one where it overcomes each and everything. So these are my two questions, sir.
Sure, absolutely, good question, right? So federated learning itself is more of an abstract concept. It essentially says that do local model training on edge devices on the local data, push the local models to a central server, aggregate it, and get a global model, right? Whether the local model training itself happens in a supervised or unsupervised manner is completely up to you, right? So FL supports both supervised and unsupervised training, right? All it requires is that the local model training can happen in a supervised or unsupervised manner, and the model aggregation can accurately reflect the aggregation of all these local models, right? As long as these are taken care of, federated learning doesn't restrict you to only supervised or unsupervised. That's one part of it, right? The second part of it, the benefits of federated learning, right? What I would say is that if it's possible to centralize data and train on the centralized data, you should do that, because that will give you better accuracy than federated learning, okay? Federated learning is only applicable for scenarios where it is not allowed or it's not possible to push your local data to a central server for training. In such cases, federated learning gives you the ability to train a global model using all these local models, but it may not achieve the same accuracy of centralized training, right? So that's the scope in which federated learning operates, right? From a research perspective, there's a lot of FL research that happens. As long as there's constraints, the constraint is that you cannot centralize data. The constraint is relaxed, then you don't need FL, right? You can actually use all the standard machine learning models. If the constraint exists, Then you can play around with your local client selection policy. You can play around with your aggregation policy. You can play around with async or sync. All these become permutations for doing further research. Okay.
Thank you, sir.
Sure. Dinesh, did you have a?
Yes, sir. Sir, I was searching on the Google about this new framework Flotilla. So, so it is available on the net or it is under the development phase, sir?
No, not yet. It's being developed. We're just waiting for a paper that we have submitted to be accepted. So hopefully in the next month or two, the moment it does, it will become open source, right? So we are hoping
I am getting new package which is Flota. It is getting the federated learning framework.
Right. No. So I can even share the link with you, though it's a private link. It's not yet available. But if you wait for a month or so and search for it, hopefully you'll be able to find it.
Okay, sir. Thank you.
Sure. Krishna Chari?
Hi, sir. My question is little mathematical. Sir, in the previous slide, you have taken average of some theta ones data.
Yeah.
So here, those thetas are for data, right, sir?
No, thetas are for the model weights.
Okay.
The thetas are the model weights for the different layers, right? T plus 1 is effectively the weight of the next version, right? Is based on the theta ones of the different local models, right?
Okay.
And the K is the number of clients that you have. So you're doing an average of all the K clients that have been chosen, right? So again, the K and N are equal. Sorry, there are different notations. But there's just a layer-wise averaging of all the weights of the local model to get the new global model layer weight.
Okay, thanks.
Yeah. Again, federated learning, the basic fed averaging is not complicated at all. It's very simple. Yes, Jackie.
So this is regarding between the server, that is the global model and the local model. Is there any discipline or the protocol is defined between these two?
So if you talk about the actual network protocol, no, there's nothing defined, right? This is just a conceptual diagram, right? How the exact protocol between the like the central server and the client depends on the framework that is being used, right? So in the case of Flotilla, for example, we just use a standard gRPC protocol between the client and the server, right? Maybe in a few years' time, there might be some standardized protocol so that irrespective of which framework it is, you can actually talk to any FL client and any FL server. But as of now, something like that doesn't exist. I mean, of course, Google has their own protocol, each framework has their own protocol, but there's no standardized protocol across all.
Thank you, sir.
Sure. Maitri?
So, sir, as you said, is federated learning most probably is used for personalized computing, sir, or generally where we can apply this federated learning? If you could describe some more examples so that we can.
Okay, so personalized. Okay, federated learning is not directly related to personalized learning, right? Because personalized learning, what would happen once you have a global model that's trained, you could do some kind of a retraining on your local data selectively to personalize it, right? But that's outside the scope of federated learning, right? Think of it in this way. So federated learning is almost the opposite of personalized learning, right? What you're trying to say is that I will do personalized learning on all the clients, but then I'll mix them all together to get a sense of what the population's behavior is, right? It's like saying that I'll look at each individual, right? And based on looking at 10 individuals, I'll get a sense of how a human being is. Let's say an alien came to Earth. They'll essentially look at 10 individuals, right? And watch them. And based on these 10 individuals, they'll say, this is how all human beings on Earth behave, right? That's what FL tries to do. It looks at the models that are trained for a subset of these clients. And based on that, it tries to get an aggregate sense of how all the data is. Right? In terms of the use cases, again, these are the use cases. In a sense, you can, anytime you want to do machine learning, where you're collecting data from different sources, right? Different clients. These could be different smartphones. It could be different sensors in an IoT. These could be different banks. These could be different hospitals, right? Anytime that the data that cannot be centralized, cannot be shared centrally, right? It could be insurance companies. Anytime you see sensitive data, where the data cannot be centrally accumulated, but you want to train a model over all this data. Federated learning is applicable. Okay.
Okay. So one more question is that personalized suggestions during that online shopping we are getting now, sir. In that context, is federated learning is happening?
It could be happening. It all depends on how the suggestions are being given, right? If the suggestions are being given based on data collected at a centralized server, maybe federated learning is not being used, right? But let's say, right? Let's say you use Amazon's app on your smartphone, right? You're browsing the different things, right? Maybe you click on a product, right? And you see it, then you click on a different product and so on. Now, by default, all this is happening in the backend, right? Anytime you click on a product, the backend knows, the cloud knows, Amazon cloud knows that you have viewed that particular product. But let's say there's a private version of that app, right? And the app itself has all these products, right? And anytime you click something, it's being shown from a local, the local app, right? Now the central cloud doesn't know about what you're browsing. It's kept private to you, right? But let's say, though the data is private, Amazon still wants to make recommendations. It still wants to recommend to people. What Amazon can do is they can send their model training to your smartphone. On that local private data, it can train a model saying that, hey, some user X looked at so-and-so product and they immediately clicked on a different product. And finally, they selected a third product to purchase. Now, this can be used by the model to train that particular local model, right? And this local model can be sent to Amazon, right? Now, Amazon doesn't know exactly which products that you chose, but it knows that a model has been trained based on your listing. So this way, you can actually use product recommendation in a privacy-sensitive manner, rather than necessarily sharing all the data with the centralized server. Okay.
Yes, sir. Thank you, sir.
Sure. Yeah. Rajshekar?
Sir, good evening, sir.
Good evening.
Sir, actually, I have one doubt. For example, we have 3-layer architecture like edge, fog, and cloud.
Yeah.
So probably where we can deploy this like model.
Yeah. So typically, right, but not all the case, right? Your edge will be running will be collecting the data and running your local model training. Your cloud will be running your aggregation server, right? That's a normal architecture. You can also have a scenario where, let's say, your edge might be doing the training and a fog might do the aggregation. That's also possible, right? A third case could be if, let's say, different banking institutions want to do federated learning, right? Then both the client and the aggregation server would be running on cloud data centers, right? Everything is on the cloud, right? So all these combinations are possible depending on the use case.
Okay, sir. Thank you.
Sure. All right. I realize that we're almost at the end of our time slot. So I'll try to sort of maybe give a quick, I believe you have another talk coming up after this, so I don't want to delay it for the next speaker. But let me quickly show you the architecture of Flotilla. So it has a central server. Within that central server, there are various components that are present. And likewise, you have many clients. Each of them run a very lightweight agent within them. The central server essentially uses MQTT, which is a pub/sub message broker, where some clients put an advertisement saying that I'm available for federated learning, and the server subscribes to that, and server maintains a list of current clients. So if a client is leaving, then that will be updated in the server. So this is a way of maintaining like a directory of available clients. Now, when a user comes in and wants to do a federated learning, they'll sort of share their model architecture along with dependency files with this server. The server will then take that and ship it to the various clients that have to be doing the local training. So there's an on-the-fly deployment of the model and its dependencies. Then the FL strategy itself will be executed. Right? The FL strategy itself comprises of a client selection strategy and an aggregation strategy. Based on this client selection strategy, it will run this on all the list of available clients. The strategy will give a subset of these clients to train on. So the server will send a gRPC call to these clients saying that, hey, you have been selected for the next round of training. Go ahead, train this global model, ship the global model also to these clients. The local agent will call, let's say, PyTorch or TensorFlow locally to train this global model on the local data to get the local model. And then it will ship it back, right? So all the trained local models will be received by this aggregation strategy, which is another component. Again, these components, there are a bunch of these components that are predefined for both client selection and aggregation, with the standard FL algorithms are all implemented. We have about close to 10 of these already implemented. or you can invent your own FL strategy also, right? So the aggregation strategy will take all the local models and then it'll aggregate them to get a updated global model. Then you can also have the option of doing a validation round. Validation round is a set of you can actually send it to the client and say that, hey, here's a trained global model, how good is it, right? So the clients will come back and say, hey, here's how good the accuracy is on my local data, right? If the server finds that the accuracy is fairly good, it might stop the training. If it finds that it's not good enough, it might do another round of training. And this keeps repeating till you either exhaust a certain number of rounds, maximum rounds, or your validation accuracy reaches what you want to get to, right? So there are a bunch of sort of interesting features. We have implemented about 5 state-of-the-art FL strategies using a Flotilla framework. We have incorporated a lot of resiliency aspects in terms of failure recovery from clients as well as servers by externalizing the state maintained at the server. We have run a lot of benchmarking experiments. This is our local Jetson accelerator cluster. We also have a 50-node Pi cluster. We have a 25-node Jetson accelerator cluster where all these experiments were conducted. And we conducted it for about 5 different machine learning models, everything from the small LeNet to a large ResNet. And we found that our framework was able to achieve the accuracy that was being demonstrated in existing papers, right? So which means that our framework is doing its job, right? We also evaluated various resiliency aspects of our framework and also the scalability. In fact, one thing that we did is we actually ran Flotilla on 1,000 clients, right? And we are able to comfortably scale to even 1,000 clients as a result. Because anytime you start getting to thousands of devices, and these are all containerized devices running on the cloud, then you're sort of starting to play in the big leagues, right? Right. So again, in the interest of time, I'm just going to jump to conclusions. If there is time, I'm happy to take more questions. I'll leave that decision to Nachiket. But bottom line, edge devices are getting very popular. Edge accelerators are getting very popular. Federated learning is getting importance in the context of privacy-preserving machine learning. There are a lot of interesting research problems with respect to how do you balance the number of rounds of training, how do you balance energy usage on edge devices, how do you modulate the performance of these in order to do more intelligent federated learning. And of course, we've done a lot of work on the framework side for FL using Flotilla, which should in the near future be available as an open source tool. As well as we've done a lot of work which I haven't talked about in terms of optimizing the edge device itself for FL workloads, but that's another big area of research for us. And you should be able to find many such papers on my homepage that talk about edge accelerator optimization for federated learning, right? With that, I will sort of stop, and I'm happy to take questions if we have time.
Thank you, Professor Yogesh. It's nice that we talk about the federated learning on edge accelerators, and many people already discussed multiple things. Just I will allow one question only, and then rest.
Maybe Jakir, you get the last question.
Sir, I'm convinced with all the explanation that you gave. Really, it helped me to get more about federated learning. Thank you, sir.
Thank you. Thanks for the comment, not the question. Appreciate it. Yeah, at the end of the day, if it even helps you read an FL paper better, I've done my job, right? So what I've done is scratch the surface, but now they should give you the background for doing something much better by reading more material. Okay. Thanks a lot to everyone. Thanks for spending your weekend evening with listening to this, and thanks to Nachiket and IIITDM Kancheepuram as well for inviting.
Thank you, Yogesh, for joining. And okay, so we'll let us thanks finally to Professor Yogesh, and we'll end this particular first session. And next session, just now we have seen the professor from CDS IISc, and now we'll see the speaker already. We have already seen in the first day is Dr. Saswati. She's a student from CDS, but in that time CDS was not formed. That time it was SCRC. So Saswati will be here with us, and she's basically from IBM, Advanced Research Engineer, and basically worked on is a team member of AI and Code project. So let us welcome Saswati for take over the session. This session I don't need to introduce more because already she is the first speaker of this session at the event. And I'm really thankful to Saswati to take the second session due to the absence of Professor Sivaram Ambikasaran due to this health problem. So he was unable to take the session. So Dr. Saswati agreed instantly to take the session, and thanks for the cooperation and thanks for the support. So Dr. Saswati can now handle. I'm just going to handle the session. Please kindly.
Yeah.
Yeah.
Thanks, Nachiketa, and thanks for inviting me again. Yeah. So this session is about applications of large language models. So I have already, I think, spoken about GPT, and that day also in the second session, one more speaker has spoken about all of this. So if participant, let me know if you do not want me to repeat these things, but I just would like to bring the background of GPT, GPT-2 and GPT-3. Then I'll talk.
Saswati, you can make the full screen. Will be good.
Oh, okay. Sorry. Yeah, is it visible now?
Yeah, it's fine now.
Okay. So yeah, so and then followed by I'll talk about in context learning, and then in the next part I'll talk about two applications where first application is about like clustering based retrieval for improved summarization in domain specific languages, and in the second application I'll talk about how we can generate question answer pair from PDF document using large language models. So participant, please let me know if I need to start with this GPT, GPT-2, GPT-3. Okay, let's get started. Let's give a little background. Okay, so at the time of when GPT came out, right, NLP trained was task-specific method, and it requires substantial amount of label data. And we have seen that annotated resources are limited in many domains, but lot of unstructured data may be available. Then there was a thought that authors thought that can we leverage this linguistic information from unlabeled data that can provide a valuable alternatives. And it was also seen that where considerable supervision is available, learning a good representation is an unsupervised fashion can also provide a significant performance boost. Proof of that is the pre-trained word embedding improve the performance of various range of NLP tasks, right? So here, author's goal was to learn universal representation that transfer to a wide range of tasks with little adaptation. And this GPT paper explores basically semi-supervised approach where it has two training procedure. First one is unsupervised pre-training, and in the next step, supervised fine-tuning. So language modeling objective on unlabeled data to learn initial parameters of the neural network model. So this is all about unsupervised pre-training. So that means you have unlabeled data like PDF documents or whatever documents you have. You just feed it to the model and get the first layer of parameters of the model, and then finally you fine tune on specific task. And then authors evaluated this on 4 different language understanding tasks. One was natural language inference. That means given a pair of sentences, task is to judge the relationship between them from one from the entailment, contradiction, or neutral, whether this one sentence entails another sentence or contradicts or it is neutral. Second task is to task they evaluated their model on is question answering, and third is semantic similarity, and finally next is text classification. So this was the background of GPT. So that means GPT was mainly two-stage training. It had two-stage training procedure. One is unsupervised pre-training, and second one is supervised fine-tuning. Now moving to GPT-2, when just before we get after GPT. I mean, at that time, the current based performing system on the language task utilized a combination of pre-training and supervised fine-tuning, right? But this method still requires a supervised fine-tuning in order to perform a certain task. And then what happened in 2018, there was a paper by Salesforce appeared, the natural language decathlon, multitask learning as question answering. What this paper does, this paper introduces the natural language decathlon challenge to explore models that generalizes too many different tasks, to many different kind of NLP tasks. And these challenges span across 10 tasks like question answering, machine translation, summarization, etc. And they also developed a new multitask question answering network that jointly learns all tasks in Deca NLP in that challenge, right? So here, looking at keeping this paper in mind, authors of GPT-2 thought, can we develop a model? Can we develop a model to make it more general for transfer learning, so that it can perform various tasks demonstrated in natural language? And that means if one model can perform various tasks demonstrated in natural language, that means it can perform a it can perform multitasking operations. So then authors demonstrate language models can perform downstream tasks in zero set setting without any parameter or architecture modification. So finally, they have trained this GPT-2 model and showed that this is, in zero set setting also, without any architectural modification, it can perform various tasks. And what was their approach? Their approach, general system. So their approach was to develop the system was like developing a general system to perform many different tasks, and they followed language modeling approach. So language modeling approach means next token prediction approach. But here what happened, what they have done is, for same input, it should condition not only to the input but also on the tasks to be performed. So that means probability of the next token prediction given the input along with the task specified. So a translation training task example can look like this, like translate to French, then followed by English text, and then followed by French text. Similarly, reading comprehension training example will look like this: answer the question, followed by document, followed by question and answer. Okay, so this was the trend in GPT-2. And how was the dataset? How the dataset looked like? Like it had a large and diverse dataset, and they scrapped all the outbound links from Reddit, and the resulting dataset web text contains the text subset of 45 million links. After deduplication and cleaning, contains slightly over 8 million documents for a total of 40 GB of text. And they removed all the Wikipedia documents from the web text. Now, how they develop how the data looks like for English to French or French to English, the data translation for translating between these two languages, data used to look like this. I am not a cleverest man in the world, but like they say in French, and then French sentence, how you will talk about this, I am not. So they give different instruction of the, can you translate it to French, or this will be in French, like that, wrote in French. See in the next sentence, it is like in a now deleted post from August, this blah blah, wrote in French. In French, how you will write, kind of. So they change the instruction and write it. And they finally, how they train this model, they actually when you do unsupervised pre-training, you just concatenate all this by input and output, separating by separator, and then at the end of one example you can put the end, but then you concatenate all the examples and then chop off in the context length and feed it to the model to predict the next token always. Okay, so this was the trend in GPT-2. Now, what happened? What is GPT-3? So in GPT-2, just you give the instruction, it will perform the task, right? So, but the thing is, after GPT-2, the authors thought like they would like to, they would like model to perform certain tasks as human do. So human do not require large supervised data set to learn from most language tasks, right? A brief instruction in natural language and few number of examples will be enough to understand. Like when you teach a small kid some summation or addition or subtraction, you just give some examples and from that they try to learn it. So similarly, they would like to teach the model through the example demonstration how it can learn. Or okay. So then finally, authors show that scaling up language models greatly improves task agnostic, few shot performance, sometimes even reaching competitiveness with prior state-of-art fine-tuning approaches. So finally, they scale this GPT-2 model by increasing model size, by increasing data volume, by increasing model architecture. Everything they increased, they scaled it high. I think 10x or something. They have scaled. And then they realized that they showed that scaling up these language models can perform various tasks with high performance. With few set example only, it can beat it can compete the fine tuning models. Now, what is in context learning? So during unsupervised pre-training, a language model develops a broad set of skills and pattern recognition abilities. These abilities recognize the desired task at the inference time. So here, if you see, there is there are three examples here in the left hand side and right hand side, three examples. But these two are different tasks. Like in the first set of three examples, circulation revenue are follows. Circulation revenue has increased by 5% in Finland, so that they label as positive. And this Panostaja did not disclose the purchase price. This is neutral. Okay, and paying of the national debt will be extremely painful. This is of negative. This they label as negative. Now they would like to get the result of the next sentence. The company anticipated its operating profit to improve. Now they feed this to the model, and then model infer and retrieve the concept. So it gets some context from this, that this is some finance news, and then it is its level is some kind of sentiment, whether it is positive, neutral, or negative. And then it says this is of positive sentiment. Similarly, in the second case, like circulation revenue has increased by 5% in Finland. This is finance. They have labeled as finance. Now they defeated the NFC championship game. This is sports. And Apple development of the in-house chips. This is tech. Okay, so that means these sentences are related to some domain. Which domain it is? It is defining that. And so finally, this is a test sentence. The company anticipated its operating profit to improve, right? So they need to infer and then retrieve from the model. So that means they just first, the model first decides which topic it belongs to. So it decided that that topic is finance. And yeah. So this is news about some topics, and it is finance related. So its topic is finance basically. So this is the output. Now what was just a moment. This is the GPT-3 model's approach. What was the GPT-3 model? Basically, its pre-training approach is same as GPT-2, including model, data training, and it is similar with scaling up of the model size, data size, diversity, and length of the training. So fine tuning means it will update the gradient in each step. But in GPT-3, there is no gradient update, but it will have kind of few set setting, right? Approach is few set setting. That means model is given a few short demonstration of the task at the inference time as conditioning, but no weight updates are allowed. And once, what is the one shot? One shot is same as the few shot, except that will have only one demonstration. And in addition to that, it will have natural language description of the task. And what is the zero shot? Zero shot is the same as one shot, except that will have no demonstration, but the model model will be given the natural language instruction describing the task. Okay, so this is the settings of approach of GPT-3. And what are the difference between these three? I mean, so in GPT-1 we have seen that it used to follow like semi-supervised approach, first unsupervised pre-training and then finally fine-tuning. But GPT-2 will have kind of along with the input output data, it will have task specification, but the training will be in the form of language modeling itself. And GPT-3 also follows the same modeling approach like GPT-2, but with scaling it up. So here the parameter count in the first case, parameter count was 0.12 billion, which finally went up in GPT-3 to 175 billion. And similarly, their training data has gone up significantly 4.5 GB to 570 GB, okay, of this plain text itself. And then there are other documents as well. So this was so here main things I would like to mention is that, like in context learning, where you just give some task specification or instruction along with the demonstration. So I'll give some examples like how we have developed some systems. Like this work is done by Baban Dibyanayan from IIT Patna. They are basically some PhD students, and they have worked with us, and we have got a paper accepted in calling. This is the paper title, like clustering based retrieval for improved summarization in domain specific languages. So I acknowledge their contribution here. So this is one of the good example of large language models. So this is actually applied in eBPF code development or eBPF code summarization basically. So what is, I just would like to briefly describe what is eBPF. eBPF's full form is Extended Barclay Packet Filter. It is a Linux kernel technology which enables engineers to build programs that run securely in kernel space. And it is used to extend the capabilities of kernel safely and efficiently without requiring to change kernel source code or load kernel models. eBPF is used extensively in various tasks, including observability, security, and network acceleration in the cloud community. So a domain-specific extension of C language is used to develop this eBPF code. And here, the natural language summaries of existing eBPF code is an important task for the understanding and development for new code. So here in this work, we investigate the effectiveness of LLM for summarizing low resource DSLs. Okay, so basically here the task is summarizing domain specific low resource languages, or we can say eBPF code. So now we would like to see whether LLM already has the knowledge of this kind of low resource languages or eBPF code. So what we have done in the beginning, we prompt the models with some domain specific functions and their related functions and variables, and ask if they are related. Okay. Note that the actual answer to all the questions is yes. However, the models are generating no. That means these models do not have any knowledge of the internal working of DSLs. or I mean they might not have seen this kind of data probably during their pre-training or fine tuning. So here these are the some function names, XDP drop. So we don't have to know much about all of this eBPF code or DSLs. So just to give you brief introduction how the model worked in the beginning. So this is the function names and these are the description, and then we query, we send all of this function name, description and query. Given a code containing XDP drop is related to PKT stop processing drop bracket is anyway in any way. So I mean this is the question given this function and description, and we get the output from these three models, Mistral, OpenOrca, Jaifer and Wizard Coder. So all of them have I mean most of them have given answer no. So that means this I mean they might not have seen this kind of data, or they do not have much knowledge about eBPF code or DSLs. Now so what is the task here, and what is our contribution? Task is mainly eBPF code summarization. Okay, so what is our contribution? We propose a clustering based approach for selecting examples in context learning. Our result demonstrate that this approach improves performance across all the tested models. And then we benchmark state of art code summarization models for eBPF code, eBPF code evaluating both zero shot and one shot settings. And finally, we see that Wizard Coder 15B achieves the best performance. We conduct a human evaluation of the generated summaries and publicly release the ratings, which can be leveraged for further tuning of generative model. So here I would like to mention that this is low resource languages eBPF code. We do not have much data for fine tuning large language models. So we would like to summarize these codes. So how can we do that? And this we have already seen that this language models, large language models, do not have any knowledge about these codes, right? So we would like to exploit this few shot setting theory, like as we have seen in GPT-3, whether we can improve the performance of the model. Now what is our methodology? We consider zero shot inference of decoder only large language models, and also we design a cluster strategy to prompt the LLMs with few shot in context examples. And this method, this clustering based method, consists of two steps. First one is source code clustering, and second step is prompt design. So in the first this first step is like we consider zero shot inference. That means we'll just send the instruction and get the summary, whatever summary it has done, and then we'll get the performance metrics. And in the second case, we'll cluster the codes, and then we'll get the best in context example from the cluster, and we will use that as a in context example and feed it to the model and then get the summary. So now this is the methodology. First step is the source code clustering. How do we cluster the source codes? So here suppose we have a set of eBPF codes C1 to CN. We extract code specific representation like R1 to Rn by passing the samples through the feature extraction module, such as UniX Coder. UniX Coder is an code language model where we can get the embeddings of the code. Okay, and these representation are obtained by applying average pooling to the final layer output of the model. This process is mathematically expressed as average pool of UniX Coder, code CI. And then in the next step, what we do after getting those representation, these code representation are used for clustering. We use here k-means clustering algorithm. And then for that, we choose we employ elbow method, which helps identifying how many number of clusters we would like to have to make. And then after clustering, we find the we get the in context example. And what at the test time, what is done at the test time, we generate the code representation using this Unix coder model, and then apply this k-means to the representation, allows us to identify corresponding cluster index. We find that code which cluster it will belong to, and we denote it by P, and then finally we iterate it over the cluster P and calculate their Euclidean distance from the test code's feature embedding, and finally we select the smallest distance, and then we use the smallest distance code as a one shot in context example for the model. Okay. And then we adopt basically three distinct strategies for designing one shot prompts. So one is random one shot, and second one is random code selection within cluster, and third is nearest code selection within cluster. So in random one shot means for each input code we just randomly select an example from the dataset and use that corresponding code summary pair as the prompt for the model. And in the second case, what we do for each test code, we extract its feature from Unix coder and determine its associated cluster. And after deciding the cluster, we randomly select a code from that cluster. But in case of nearest code selection within the cluster, actually in the first step we find which cluster the test code will belong to, and then finally from that cluster again we choose the nearest example as a one shot in context example and use that as a prompt. Now here we have shown the flow diagram during the test time or inference time for a query code. At the test time, this code will be passed via Unix coder baseline model, and then we'll get the code representation of the model, and we'll get to know which cluster it will belong to, cluster it will belong to, and then we get the summary of that particular associated code. We have code and summary we have already. Okay, and then we generate our prompt like this. So this with 3 hash human, this is actually system prompt we have used this 3 hash human, and then 3 hash summary, and then we use this summary, and finally this is our test code. We pass this test code and pass all of this as our generated prompt and feed it to the AI model to get the final summary. So this is our flow diagram. And what is the experimental setup here? Actually, we had very limited data. We had total 160 functions that also were annotated by students and professionals with sufficient domain knowledge, and unique. So, so if you see this is the result. This is the result, and here we have actually we have used various large language models, starting from DeepSeek coder, and then CodeLlama Instruct, Wizard Coder Python, Mistral OpenOrca, Jaifer Vita, and Wizard Coder. So these are these models we exploited for this summarization purpose. and this model has parameter 7 billion to 15 billion. These will have only 7 billion parameter, but wizard coder has 15 billion parameter. And these are the BART, Rouge 1, Rouge 2, Rouge L, and BART score. Okay, for all of this, where we have taken all of this, we have considered all of this model. This is for zero sort, and right hand side columns are for one sort, random one sort, and below table is left hand side for random code selection within the cluster, and right hand side columns are for nearest code selection within cluster. Now we can see in case of zero sort, how the numbers were. If you consider only blue score, you can see this blue score itself has increased from 4.2 to 4.8 in case of wizard coder, and similarly it increased for all of the models. Okay, and it continuously increased from random one sort to random code selection within the cluster. It has improved from 4.8 to 7.9, and then finally when we choose the nearest code from the cluster, we get blue score of 17.7 in case of wizard coder. And we have seen that wizard coder also has the best performance across all the case of sorts. I mean, zero sort, random one sort, all of these sorts. And yeah, so this is the case. But in case of 7B models, it is not kind of consistent. In some cases, like Mistral Open Orca is performing best, and some cases Zypher Beta is performing best, but not always. Okay, but we can see as this wizard coder model is the biggest model among them which we used, and this is performing best across all the models, and it is continuously increasing from zero sort to nearest code selection within the cluster. So also actually we evaluate code summarization manually as well. Evaluate code summarization is basically challenging due to the varying level of granularity at each as each summaries can be written in different types, or summary writing is very difficult, and evaluating also is very difficult. So manual intervention was needed to verify the accuracy defined by those kind of blue scores or rouge scores. So here we have given 90 code summary generated by this model to 4 different experts, and then the rating were from 0 to 4 scales, and higher score indicates a better quality of the summary. Here we see the as per manual evaluation, we see that Zypher Beta is performing best, and average score is 3.02. So here we proposed a straightforward clustering based technique to retrieve functionally similar code, which serve as in context example for effectively querying LLM to generate eBPF code summaries. And experimental results demonstrate that our approach improves the summarization accuracy of various LLMs by 12.9 blue points over the random one-shot examples. Yeah. So this was one example, and another example can be generating question answer pair. So I have worked on this problem. So this is basically actually what happened when we train or fine tune or instruction tune certain model in the form of question answer pair. We have seen these models perform very good in some cases. So we would like to verify whether we can also improve the performance of our model's performance. So we have PDF documents of various COBOL documents. Okay, here our task is to translating COBOL language to Java language or COBOL summarization. Now we have these PDF documents. We extract in the first step, we extract this text and then figures and tables separately, and create document chunks with specific size, And then we separately have Excels and PNG files for figure. And Excel files will be generated from the tables. Now we prompt engineer give our prompt to the LLM to finally get the question answering pairs. And after post processing, we filter some of the keywords which are very short. I mean, the answers of the questions which have very short answers. We filter those and then feed it to the large language model for further training. So what are the steps here? We use here deep search or Adobe PDF extra to parse this PDF to JSON files. So we in the beginning we have PDF files. This PDF we extract. We have two parsers, like one is IBM's deep search and another one is Adobe PDF extract. You can use any one of them, and then we'll get the text extracted from all the text, and tables will be segregated in Excel files, and figures will be segregated in PNG files. So then from that JSON file, from the text, we generate document chunks of specific number of words, like 500 or 1000 or 1500 words, and then we generate question and answers. So here what we do, we have this PDF documents, we have JSON structured from the text, and finally we drop a text element. If the text element contains figures, tables, etc., we drop all of this. And then we create this 500 or 1000 word document chunks and give it to the LLM for with our prompt, and then get the question and answers. So we have actually 11 number of PDF documents. Approximate number of pages processed was 8090, and number of document chunks we found 5224, and then number of QA pairs were 66,658. And then from that, when we pass those document chunks to the large language model, here we use Mixtral 8x7B model, and this model has 47 billion of active parameters. Okay, so what was our prompt in the beginning? For the zero shot prompt, to use this, you were asked to come up with a set of 15 diverse question answer pairs on the given passage. The passage is about a concept of COBOL programming language. Please follow this guidelines principle when generating responses. So we have given all of this instruction that use the proper grammar and punctuation, always generate safe and respectful content, do not generate any content that is harmful, etc., and always generate content that is factually accurate as per the given passage. So that means you don't give anything from outside. The question answers should be clear and human like. So these are all our user supplied prompt. Okay, and then we pass the passage, like to has given passage, and then we feed this 500 word document passage, and then we tell this question and question colon and answer colon, and then we see that it generated this kind of question and answer pairs. And so it generated 15 or 20 question answer pairs like this. What is the purpose of passage? The passage explains how to retrieve messages from queue using COBOL programming languages, specifically with XML table function. So these are very small question answer pairs. You can see one liner question and a one liner answers, right? So what we do, we have after that we have taken those generated question answer pair, and then we fine tune those on that data, and finally got a kind of instruction fine tuned model. And then what we see when we inference, we notice that generated summaries are very short but not comprehensive. Okay, so how can we improve? How can we teach model to generate longer summary or answer? Train the model QA that have comprehensive answer. So that means that means what, we fed this kind of small question answer to the model to get the final model. So model has learned to generate all these small question answer only. So because it did not see any large question answer, so it was producing that. Now how can we get the get the model which will give us better answer or some comprehensive answer? So for that, during training we have to feed those kind of question and answer with comprehensive answer, or long answer, long kind of answers. So we generate longer QA pairs using this model with the given two prompts. Okay. Now, what was our kind of prompts we used next? So this is the basically instruction system prompt. System prompt is used for those that Mixtral 8x7B model. Can you this you can see in the beginning angle bracket is an inst. So this is used as a system prompt. A system prompt basically is a set of fixed instruction created by the developers to constrain the LLM's response. And at the end also it is given like one third bracket square bracket slash inst. Like this it we need to finish it the system prompt. So how was our prompt look like can you help me create question and answer that explain basic COBOL concept from the provided document? So then we give some guidelines, please follow below guidelines while generating, and then we give the document. Document means a big passage, kind of 1,000 word passage or 1,500 word passage. And then after that we give two question and answer. I have given example here, one example I have given here, like the example which talks about generating code, COBOL code, and another question I had given to summarize the COBOL code. Okay, so one is opposite to the other. And then question answer, and we put one end, and then whatever we generated those 1,000 chunks or 1,500 word chunks, right? We feed those documents here and get the question and answer pair. Now the question and answer pairs were little bigger than the earlier one, not the one liner question answers. So now after sending this prompt, few short prompts, we get this kind of question and answer. And now when we train the model with this kind of question and answers, we get now we get the during inference time also we are able to get little bigger or comprehensive answers. So now in the next step, like can we also generate question answer from the flow charts or figure? We can, yeah, just take the PNG files. We have tested this. We have taken the PNG files and convert these figures to RTF, and then feed it to the model, and we are able to generate question and answer. Like this was also tested in the Mixtral 8x7B model. So suppose this is the this is one flow diagram here. It is given as a PNG file. Okay, and if we take the TXT version of this PNG, it will be looking like the middle box here. So if we send this to the model and say generate 10 question answer pairs from the following, and then it was able to generate few questions and answer. What is the command for setting of variables, first occurrence, etc. So so model can generate, they are capable of generating question and answer from figures as well. Yeah, so why I was talking about mainly those first work like summarization of eBPF code, those kind of work possibly and probably, they do not take much computing power, though you need to run model inference on 15 billion model, but you don't have to train any model. I know in various research institute we do not have that much computing infrastructure where we can train large language models and even fine tune large language models. But with 1-2 GPU also we can run our inferences. So yeah, so that was one motivation why I would like to show this kind of work where we do not need any training, only inferencing also we can work, and we can show the improvement of the model with good in context example. If you supply good in context example, you can improve the performance of a model. Yeah, I would like to end my talk. Sorry. You can ask some questions if you have.
Thank you, Saswati. The participant, if you would like to ask some questions, if you have any queries to this or any discussion you would like to do.
Good evening, ma'am.
Yeah.
Ma'am, thank you so much for the session. I was following the LLM's topic from our last session, and I have two questions. In the last time when you gave us this session, you specified at some particular point that LLMs are seen like kind of black boxes, and they have biases even after training. And if that is the case, now how can we actually justify in some particular, now like if this for mixtural, if it is like we are even after giving prompts, let's say some of the question and answers, in the question and answers, if it goes out of the context, and how can we justify that? Do we have any particular opening going in that in that way where we are actually rectifying this, and also the second thing is and also in the last time there was something like every time the LLM has to be it has to for every prompt it runs again and again. So how can we hold that particular session go on for a longer time or in a longer memory, if you get my point?
Second point I did not get. A first question, if I understood correctly, like you are saying, if the question and answer, if the generated question and answer does not follow the context, if it goes out of the context, how do you validate? Is it so?
Yes,
Or-
ma'am. For the first one, the second one is like you have I want to say shorter memory, like it is kind of, how you say, stateless.
Okay.
That I guess that's what that is what the word was used, but I wrote it down as stateless. I'm sorry if I'm wrong. I have written it down here in my notes as a stateless. The most of the LLMs are stateless and they have shorter memory. So is there any scope we are looking into to make them retain the session, or to run the prompts for a longer memory or something something like that? That is my second question.
No, so this prompt, yeah. So so this Mixtral model, I think it has 128K of context length. First of all, it should. I mean, my prompt was longer. Prompt was longer in the sense document was longer, and I had, two question and answer along with that. So you need to feed the model in the context. Fit whole prompt instruction in the context lens. So you need to choose such a model which has that capability. So various models does not have that capability, so that you cannot use you cannot use here 2048 context length. So here I think this model Mixtral 8x7B model has 128K context length. That is why we have chosen this model. And so that is why mainly we have chosen and first question, like how can we know whether it is not following the context? So that you have to do some kind of filtering, or nowadays LLM, as the people are using LLM as a judge. You ask another LLM, how is your generation? I mean, I don't know how good those are. I mean, how good metric those are. But basically, manual validation ki whether your generation is correct or wrong. Actually, when I was generating this question and answers for this, and a small question answer, you can validate, because this answers you will find itself in the passage. So by that you can validate, okay, your generated answers are correct. So actually you can validate by calculating some of the metric, like this blue score or red score, some kind of metric you can apply, and see if how much ever your percentage I mean answer is there in the passage or not. Or you can also use LLM as a judge. Now people are using LLM as a judge. LLM itself will judge how good the quality of generation. Yeah.
Thank you, ma'am. Thank you so much.
Yeah.
Any other participant would like to discuss, can ask some questions.
Do you have any other question? Actually, last day somebody had asked, I don't know whether that participant is present or not. Somebody asked, she has some MongoDB database, she would like to generate a data or something.
Yes, ma'am. That was me.
You were okay. So, what was your question? You had a MongoDB database. So, MongoDB database had what data?
No, ma'am. So what kind of databases we were database structure we were, if we are using a Microsoft SQL Server or a MongoDB or something like that, what we were using to actually connect with all these data sets. That is what my question was.
Oh, okay. So that no. So these are basically, these data sets basically are in the structured format, right? How they would like to generate their data. I mean, it depends on the tasks. So suppose you have some SQL database where you have some table, and now suppose for the task natural language to SQL generation task you have, okay. Now you have a natural language query, and so these are basically, earlier it used to be done by crowdsourcing. I mean, people used to manually sit and then used to generate the data. Like you some expert person used to sit, okay, you ask some questions, and then you find the SQL query from that table itself, and the question, it's a natural language question itself also in the from the table. So you can get some kind of data from that table, SQL table. But those data set which are available, those are completely different from whatever you are saying, like SQL database or MongoDB. Those are not that kind of data. They will have some specific structure.
Okay, ma'am. Thank you so much.
Okay. I hope I could answer your questions. I'm not sure. Yeah.
Yes, ma'am. I got that. Thank you, ma'am.
Okay.
Okay, so I think hope the participants have already asked some their queries, and if anybody also would like to interact with ma'am, they can reach her LinkedIn profile and connect with her and interact with ma'am, or anything you would like to collaborate, you can definitely talk to her. With that,
Yeah,
I would like
if
to thank.
anyone is interested, you can reach out to me. My email ID is sdana027 @in.ibm.com. Yeah. So if anybody wants to work on this, we have some kind of GRM project where students work on those they don't get paid or anything, just for their interest. And if
Ma'am, can you type your mail ID, please? Can you type your mail ID, please?
yeah, it's the chat. Hybrid LLM in the sense, I didn't get what is hybrid LLMs? What do you just see? Is there any hybrid LLMs? What do you mean by hybrid LLM? I didn't get your questions. I mean, I don't know what kind of hybrid you would like to mean. Which different aspects or missions? I mean, are you saying LLMs which can perform different tasks, right? If that is so, then these large language models are developed for that. You just give some demonstration of the task, and you see whether it is able to perform your task or not. And if it is not able to perform your task, you just see how good your in context example is. If it is not very good with respect to your test example, then you try to think some kind of algorithm by which you can get the very close data, or which you are using during test time. Does that
Okay,
answer your question?
So we are running short of time. So Saswati, we can now allow those, because you have already shared the email ID, so they can reach out to you in case they have any discussions further. We again will thanks Dr. Saswati for having the second session, and I mean, really hope the participants in the first talk itself, the participants have good reactions that lead to again to invite you, and so they have really get benefited out of your expertise. Thank you, Saswati, again.
Thanks, Nachiketa. Thanks to IIT, IIITDM Kancheepuram, and thanks to the coordinator and you for giving me this opportunity and inviting me for this nice forum.
Thank you, Saswati. With that, we will close this second session of this last day. Next speaker is already waiting here. I mean, so we'd like to, before inviting to talk, so I would like to introduce. So once again, come back to this last session, and so before we invite Dr. Parikshit Ram, it's my privilege to introduce to him first. Dr. Parikshit Ram is a principal research staff member of IBM Research, with a broad research interest in similarity research and efficient all pair of algorithms, density estimation, computational geometry, and automated machine learning and data science, among others. He currently conducts basic mathematical and applied computational research on topics pertinent to optimization, as well as various aspects of generalization and learning with less data. Prior to joining IBM Research, he was a senior research staff member at Skytree, a machine learning company focused on providing high-performance machine learning tools for large-scale modeling and data analysis, which was subsequently acquired by Infosys. Dr. Parikshit received his doctorate in machine learning at Georgia Institute of Technology, and bachelor and masters in mathematics and computing from Indian Institute of Technology, Kharagpur. He has been in program committees and senior member committee of top conferences, and recognized as a top reviewer at ICML and NeurIPS multiple times. with this small introduction, I would like to hand over the session to Dr. Parikshit.
Thank you, Professor Mishra, for inviting me. Hopefully, you can hear me clearly.
Yeah, I can hear you. Yeah.
Yeah, I will go ahead and share my screen. Okay, are you able to see my screen?
Yeah. Yes.
Again, first, I want to thank you, Professor Mishra, for giving me this opportunity to speak here and for organizing this exciting workshop. And I am very privileged to speak to you about what I think is the critical role of fundamental mathematical tools on the path of AGI. So I am part of the Mathematics and Theoretical Computer Science group at IBM Research, and our research lab here in the US spread across 3 different locations, one in New York, one in Massachusetts, and one in California. And our focus is on like we really are focused on the mathematical aspects of artificial intelligence and AGI, or what's known as artificial general intelligence. So I will actually begin by talking about what I think is general intelligence, and then I will talk about how various mathematical tools can help us get there, because we are of course not there yet, but can help us get there. So just to begin, so what is general intelligence? So a few years back, Francois Chollet had this paper out called On the Measure of Intelligence. And based on that paper, he set up this ARC prize, or an ARC competition. And one of the things that he focused here is on this question of general intelligence. According to him, and this is what I agree, is that general intelligence is the ability to efficiently acquire new skills. So what we think of as AI right now, pre-LLMs, was that we were creating systems that could acquire skills. But general intelligence is something that is the ability to efficiently acquire new skills. And if you're interested in this challenge, you can go into the QR code on the top right, and you'll find more information there. But I want to first distinguish what it means, what's the difference between learning a single skill, or ability to learn a single skill, and ability to efficiently acquire new skills. So if you look at this example here, we have on the left a picture, and then the right is what's the output picture. So this is one example. Then here's another example. If you look at these 2 examples, you're trying to think, what is the change? What is the function that is being operated, which goes from the left to the right? What is changing? And then as a human, I think many of you might have been able to figure this out, but for a machine, we would have to give it a bunch of these examples. And then given large enough training set and expressive enough model class, we learn how to identify objects in this picture, how like the red square is an object, the blue pyramids are kind of objects. Then the machine learning also has to learn this notion of above and below. And then finally, it has to learn to move the object that's on the above down to the below. And once it's able to learn that with enough examples, it can then solve this new problem where it has to move the green objects below the yellow objects. So that's one skill, being able to move objects from above to below. Now here comes another problem where my input is on the left. It's somewhat of a unfinished rectangle, and on the right is where we have a completed rectangle. Again, there's a second example, and so you see like this is the pattern. But again, if you're training a model, we would have to give many such examples. Again, learn the notion of objects, learn the notion of incomplete and completeness of an object, and then finally complete incomplete objects. So this is again, and once the machine learns that, the model learns that, it can then solve this new example. So this is what we think of as ability to learn a single skill. But what is acquiring? What does it mean to acquire new skills efficiently? So one way to think about it is you want a machine or a model which takes these demonstrations and is quickly able to learn the above and below transformation and apply it to a test example. And then that same machine, same model, can again look at these demonstrations and be able to learn the notion of filling in the center. And then also learn how to clean up an image, where you have some image and some noise, and then you have to, the demonstration says, okay, you kind of remove the noise, and then you can, but very, very few examples. And similarly, you have the complete shape example, extract objects example. These are all new skills that the model needs to be able to acquire very efficiently with just very few examples. And that to me is the notion of acquiring skills efficiently. And in that case, what is it that we want the model to be able to do? Or what is the learning task here? The learning task to me would be like, given some data set, some training data. Again, we have to specify what this training data should be, and I'll get back to this later. And a model, again, the details of the model we will discuss later, but we need to learn a model or a system so that given very few examples from a skill, we're able to acquire the skill using the model and then successfully apply that learned skill on new examples. This is at least what I would think is a general intelligence. And at least for the most part, we consider ourselves humans as generally intelligent. And the interesting thing about this task is that it's easy for humans, as you could see when I was walking through the examples, but it's hard for AI. And this is not just me saying it. There actually has been a clear evaluation of this. So on the left over here, if you focus, these are like the scores of at least the top score of humans. And the center two columns are the Kaggle scores, because it's a Kaggle challenge that is running actively. And the right two columns kind of show the performance of GPT-4 with varying temperatures. Of course, there's new versions of these large language models coming out, and they will be evaluated, and their performance does get better, but it's nowhere close to human level. And also, we have to remember the amount of investment that goes into building these models. They are not cheap. Millions and millions of dollars and engineering resources are spent into building these models. So, and if you're interested more into these, about these results, you can look at the paper that I have at the bottom, or just point to the QR code on the top right, and it'll get you in the right place. So, to me, this is the path to AGI. It's very simplified. So of course, this is not as straightforward, but I'm just simplifying it for presentation. But we know as a community with machine learning and AI how to learn a single skill well. Given a large enough training set and an expressive enough model class, we know how to acquire a skill efficiently and apply that learned skill to unseen examples. Whether it's computer vision, natural language, we have been able to do this. what I think we should try to get to is learning to efficiently acquire a new skill. Given some data set and some model, we want a system that, given only a few examples of a new skill, can efficiently acquire that skill and apply it to unseen examples. And the acquisition of this new skill can be done by many different ways. It could be like a fine-tuning of a model. It could be a program search if your system is a program synthesis system. It could even be in-context learning, which one of the previous speakers mentioned, where you pack in your examples in the context of some generative model and hope that it processes that and acquires, quote unquote, acquires the skill. Those are different ways of doing it. I don't think we are there. We are able to do this successfully yet, as the numbers show, but there are many ways to acquire a new skill efficiently. But going back to how we learn a new skill, let's look at what usually was our goal there. The goal there was to minimize some notion of a loss. Like it could be mean squared loss if you're doing regression, some kind of cross entropy loss if you're doing classification, perplexity if you're building like a large generative model. And we want this loss of the model that we have learned, which is F here, to be low on unseen data. So like not just on the training data, but some new data you give me from that skill, my loss should be low. And usually this is like a meta algorithm of how we learn such a model, right? Like, so we are given some skill data. We are given a model class, whether it's neural networks, linear models, decision trees, what have you. We start with some model in my model class. We perform an inference on it, but some data from my training data, and you predict with the current model. That allows us to compute a loss, and then we update our model based on that loss. And we do that until our learning budget runs out. And the final model that we get is what we say is our model that has acquired the skill, the trained model. So effectively, we are solving this optimization problem where we have an empirical skill data distribution, like the training data. We pick some model class, some gigantic neural network, or just a small decision tree, a linear model. And then we solve this optimization problem. And it could be continuous, it could be discrete, it could be many different forms of problems. But if you go back to our original goal of low loss on unseen data, that is usually only possible if we have enough data from the skill, the model class is expressive enough, and we have enough compute resources to solve the optimization problem efficiently. If we didn't have the compute resources, we wouldn't be able to train gigantic models on gigantic amounts of data in a reasonable amount of time and get strong performance. So enough compute resources is also a critical aspect. Now, how does that paradigm fit into the learning to efficiently acquire skills problem? Can we use that same paradigm? And there is some work that has kind of started pushing along these lines. There's like about 7 years ago now, there was some paper on meta learning. If you've heard of something called MAML or model agnostic meta learning. But there's also more recent works on test time training of these large language models. The whole idea there is that we want to, given some few examples from a new skill, we are allowing a model to be efficiently adapted. So there's some kind of few shot adaptation that goes on. And that adapted model, which we are saying as G star F, where F is the original model and G star F is some adapted model, we want to see low loss on unseen data from the skill for that adaptive model. And if we want to solve this, like have this as our goal, the goal mathematical problem, how do we fit that in our usual inference loss computation model update framework, which is how we know how to train all our models. So again, looking at this problem again, one of the ways we can make it fit into this framework is now not only having a training data distribution, but also having a training skill distribution. So essentially, we will have not just a single data distribution, but we will also have a set of skills that we are training our model to learn during the training phase. And again, we followed the same process as before, where we pick a model class, we initialize it, and then the inference step itself now is a little bit more sophisticated, where we have to first sample a skill, get some few demonstrations from that skill, and adapt the model with those demonstrations, and then do a test on that adaptive model, and then compute a loss. And then, given this loss, we then update the main model F to reduce this loss. This would be like the new framework for like a meta algorithm to train a model to be able to acquire new skills. And if I want to write that algorithm, like the optimization problem, what that algorithm is solving, it would look something like this, where we essentially have an empirical skill distribution, this tau hat, t hat. We also have some data from each of these skills. So imagine the example that I was showing you earlier of these images, whether it's center or cleanup, complete shape. So I would have a set of skills that I have available, and I have some data from each of them. And then we pick some giant model class, which we wanted to be able to acquire all those skills, but also generalize to new skills. Now, this whole problem is something called a bi-level problem. So if you look at it, there are two minimization problems. Not only do we have to learn a model, which is the upper level optimization problem, but for each skill, we also want to solve this lower level problem, or this adaptation problem. How do we quickly adapt the model to a particular skill and do it efficiently? These bi-level problems are usually much harder than the standard single-level optimization problems that we study in literature, in machine learning and AI. And again, to come back to our goal, we want our model to be able to few-shot adapt to a new skill and have low loss on unseen data from that new skill. And to be able to do that, we again need a very expressive model, but we probably need a model which is way more expressive than the standard models that are used, let's say, for vision or so on. And large language models can be thought of as maybe something that's expressive enough. We need enough skills to do the training. Otherwise, like without seeing a lot of variety in the skills, we will probably won't be able to generalize well. But with the star, I'm kind of denoting that this is a new requirement if you want to solve this new problem. We also need more data, but also more data from each skill. So not only do we need data from one skill, we have to have access to data from all different skills. And finally, we again need enough compute to be able to solve this bi-level optimization problem efficiently. But this is not how these large models are trained nowadays. Like nobody trains it with this kind of a setup. Usually, the way it's solved is that we kind of find a large enough, very varied training set. So like pretty much everything on the internet is like one option, right? Like the things like the pile, and they're like these gigantic corpuses. And then you pick some giant model class, like a large language model with billions of parameters or what have you. or even like ensembles of LLMs where you have each is like small, but together they are gigantic. And then you train the model on a large corpus for some auxiliary task. So like one common thing is you kind of, it's called pre-training, where we pick some loss, which is not related to any specific skill, but it's just something that seems like a reasonable loss, like next token prediction, right? Like that's something that we commonly use to train these large language models. And then after we have done this pre-training on this giant corpus, spending a lot of compute, a lot of engineering effort, we then do some kind of fine-tuning of this base model to acquire some variety of tasks and skills. So this could involve some kind of a RLHF or reinforcement learning by human feedback. So you're training it to be generating outputs that's more preferable to humans. You do some kind of safety alignment or preference optimization. You can also train it to do like code completion and things like that. Or, for example, the latest models that have been out, they're supposedly trained with some kind of chain of thought way of responding, where they're not only trained to predict the next token, but they're trained to solve problems, and they're given kind of a step-by-step solution of the problem, and they need to be able to generate step-by-step solutions. So you can fine-tune them for that task. One critical aspect here is that there is no bi-level structure here. So we are not explicitly learning to acquire skills, but it is efficient. It's a more efficient way of solving this problem. Of course, we are not solving the problem which I think is the right problem. And for a new problem, with enough data, we can try to fine-tune this model or use adapters like LoRa or low-rank approximation. Or there's new things like Galore, which are approximating the gradients instead of the model weights themselves. So you do some kind of, you modify this large model. But if your data is small, you just usually pack it into the context, and you hope that things work out. Sometimes they do, and most times they don't. And you have to kind of do some kind of prompt engineering to make things work, which, again, it's a subjective matter whether you consider that an intelligence or not, if you have to do the work to do prompt engineering to get the right answer. But coming back to, if we want to solve what I think is the right problem, which is this bi-level problem, it's a very hard problem. So it's not straightforward that it will be like easy to solve. Definitely will be harder than what we are solving right now. What I want to share with you is some angles of attack that I've been working on for the past few years, which I think will be useful here. So first, I will cover something called robust multi-objective pi-level optimization, which we can theoretically show gives us better skill generalization, which means that we can learn a small number of skills and generalize to unseen skills better. Then there is this notion of distributed representation dense associative memories. I'll get into what dense associative memories are, but this is a way of getting better expressivity and size trade-off. So we don't need really gigantic models. We can get better expressivity even with smaller models. And then, as we can see, that to solve this problem, or even to train the LLMs that we train in today, we need a lot of data. But I want to convince you that in many of the problems that we care about, such as language, there is a notion of compositionality in the problem. And that's something I will explain what compositionality is, and I think that is the way for us to get around this immense data needs. We can generalize well without needing large amounts of data. Now, again, so coming back to this problem that that I think is the right problem, we can rewrite it by changing like the expectation over the scales with just a summation and kind of putting it all together. This is what's commonly known as the stochastic bi-level optimization problem. And it's recently it's been studied in like optimization OR literature for a long time, and has been of high interest in the machine learning AI community in the last like 5-6 years. And if you go to the QR codes on the top right, these are some tutorials that people have organized in top AI machine learning conferences. And these are good introductory material if you want to learn about what is bi-level optimization and what is stochastic bi-level optimization and some algorithms to solve them. And bi-level optimization generally themselves are very hard and can be strongly NP hard. So they're extremely hard problems. But they have many, many applications in machine learning, whether it's representation learning, hyperparameter optimization, reinforcement learning. They have seen even interest in like fair learning, where we want to kind of train models which are fair across demographics. And then there are many other applications here. And it's an active area of research for efficient algorithm development and analysis. And the goal there is to get to an algorithm which has the same kind of convergence rate as like a algorithm for a single level problem, and can match the computational overhead of something like the stochastic gradient descent algorithm, because that's very desirable. Everybody just goes to like PyTorch and just says SGD or Adam or what have you, and uses that to train the gigantic model. Nobody even thinks about writing their own optimization algorithm anymore, because that's how efficient and simple they are. But sorry, I do see a raised hand. Is Professor Mishra, should we take questions now? Or should we wait till the end?
We can wait till the end, I hope. It will be better.
Okay, thank you very much.
Please, participants, please keep your questions. We'll discuss at the end.
Okay. Thank you. Yeah, so if you want to learn more about this area, especially its interest in machine learning and AI, these QR codes will take you through some really nice tutorials. Not by me, but like people in our field who are really working deeply in this. But usually there is, like, this is again like a meta algorithm for solving this bi-level problem. And the usual way is, there are a couple of ways. So the first way is what's known as the double loop algorithm. So you have an upper level objective, I'm calling it U, and a lower level objective, I'm calling it L. And you start with some corresponding upper level variable F and G, and lower level variable G. You fix F and then you solve for G. And then given G, you update for F. And then you do this iteratively. So it's like a double loop. So you're in each outer loop, you solve the lower problem to some approximation. And when I write something like this is just saying it could be some kind of gradient-based or second-order based update step. And it's easy to implement. And practically, they tend to have faster convergence, but they are computationally expensive. Alternately, there is something called a single loop algorithm, where you update the variables, both the upper and lower level variables, only with one step each. So you have one single loop, and you update the lower level variable, and then you update the upper level variable, and they're computationally cheaper. But one tricky thing is you have to handle things like learning rates for your optimization very carefully, otherwise things can diverge. Oh, sorry. Sorry, give me one moment. I'm not sure why the screen share just stopped. Sorry, apologies.
Yeah, it's fine.
Let me try this again. Okay. Yeah, so I was talking about the single loop algorithms. They need like careful learning rate handling for fast practical convergence, but they're actually computationally very cheap. And if you can set the learning rates properly for your problem, they are very efficient. They can be very efficient. They're almost like running SGD. But one of the challenges with these bi-level optimization, which I didn't get into the details of, and it would be good if you get in, look at these tutorials, they'll give you more details, is that computing the right gradient or the right update requires second order information. And you can show that if you don't use the second order information, like the Hessian or the Hessian or the Hessian inverse, you will not converge. It's not like gradient descent where you can converge even without the second order information. In these cases, in certain scenarios, like you need the second order information, which makes bi-level optimization practically hard. So this was just standard bi-level optimization. What one of the things that we study is, if you remember, as I said, like we have a task distribution. Now, instead of optimizing for the average performance across all skills, which are denoted by tau, what if I optimize for the worst case? So this objective right here is the worst case objective, that I'm going to force my model to learn in a way that it's optimizing for the skill that I'm worst at. So I'm trying to do something, it's called robust optimization, or in this case, it'd be robust multi-objective bi-level optimization, that I'm forcing the learning to focus on the worst case problem. And of course, like, just remember that this is worst overall. So you don't just pick one skill and be worst case on that. What is the worst case will change as your learning happens. And this is something that we study in this paper, min-max multi-objective bi-level optimization. This was at ICLR, International Conference on Learning Representations in 2023 with my co-authors here, Alex Sangta and Shu Wei. Again, the QR code will take you to the paper itself. And why do we want to optimize for the worst case? What we can show that theoretically, you can kind of talk about performance on a new unseen skill. Like, what is it that we might be, how well will we perform on a new skill is bounded by our robust objective, this worst case, worst skill performance, plus some other complexity terms that comes when you do this kind of analysis. But our robust objective is one of the terms. And if we minimize that, we're minimizing the right-hand side. And solving this robust problem is even harder than solving standard stochastic bi-level problem. But here's an advantage. So this is an example where we train the model, and then the blue and the red lines show the performance of the robust objective versus the objective that's just computing the average, and on skills that are seen. But the green and magenta lines compare the performance on skills that have been not seen. So these are new skills that I'm asking my model to be able to learn with few examples. And in that case, we can see that this robust objective allows us to get, in fact, 10x better performance. And again, the y-axis is in log scale. So this is mean squared error, but log of that. So that means it's almost like 10 times less, like 1 order of magnitude less mean squared error here. So that's the potential advantage of solving this harder problem. And then the way we solve it, I'll just get into a very small technical detail here, is that we essentially replace the max operation with a simplex constraint and a maximization on that simplex. So what is a simplex is essentially it's a set of scalars, lambda taus, and then they need to be positive and they need to add to 1. And when you take a maximum over these variables, the weighted sum, which are weighted by this lambda, what we end up getting is it's the same as the max, except we have kind of made the optimization problem more continuous. Instead of the max, which is a very discrete operation, we have kind of softened it with some constraint, with a constrained version of the problem. And so the simplex constraint allows us to convert this max operation over all the different skills that we have in a training set into a sum operation. It's a weighted sum where the weights are something that we are also optimizing over. And they can be sure that these two are equivalent problems. And based on that, we have a very simple single loop algorithm, again, where we update the lower level variable, we update the upper level variable, and then we update the simplex variables as well, which is allowing us to figure out what's the worst case objective as the program optimization is progressing. So in some cases, the objective that's the worst case will change during the optimization, and this takes care of that. And we can show theoretically that the convergence rate, like the number of steps we need to get to like some epsilon convergence, is of the order of the square root of n, where n is the number of skills that we have in our training set, and divided by epsilon to the power 2.5. So like smaller. So it's not the best rate, because standard SGD rates you can get to even 1 over epsilon, not 1 over epsilon to the power of 2.5. So this is slower than that. But our empirical evaluation on some data sets says that our bound is not that far off from what it actually does. And we also, one of the factors here is the square root of n over here. So what this is saying is that as we have more and more skills in our training set, the convergence will slow down. And the plot on the bottom kind of highlights that when we have only 4 skills to learn from, we are converging faster than when we have 64 skills to learn from. Our convergence rate slows down like significantly. So it's not it's our contributions here were like we were able to get better generalization on unskilled objectives or unseen skills, and so we effectively need fewer skills to train to generalize better. That's a positive. And the mathematical tools that we used here were like robust optimization and bi-level optimization, both for algorithm development and analysis. But of course, there are open questions here. Where like if we have more and more skills, which is the world we live in now, we are training these models with gigantic amounts of data. So we probably want to train them with as many skills as we have. Convergence is going to be slow, at least with the algorithm that we have. So better algorithms are needed. We also need to be able to evaluate all these skills repeatedly, which has a significant computational overhead. And we are hoping that there will be ways where we can like sample skills in a more strategic manner rather than look at all the skills all the time. And the last note, in which is something I already mentioned, is that the rates are still slower than standard stochastic gradient descent style algorithms, where it's instead of being 1 over epsilon, it's 1 over epsilon to the power 2.5. So that's definitely slower, and we want things to be faster if we really want to solve the bigger problem efficiently. But coming back again to this bigger problem that I think we should try to solve. One of the critical aspects was the model class. What kind of model should we pick? Right now, we have these gigantic models with like transformers-based models, which have been seen to be extremely expressive, but also are very parameter heavy. So you have like gigantic number of layers, each layers with large number of parameters, and your overhead for inference or overhead for training grows with like the context length. So you have all these there are different challenges. Alternately, there are these things called the associative memory networks or Hopfield networks. They are what's called energy-based models, and I'll get into that more. And they're related to something called spin glass models from physics. I'm not an expert in physics or spin glass models, so I won't discuss that. But if you're looking for information, you can kind of search for these keywords. It's a kind of a recurrent network where the input is recursively updated through states to get the output. So it's not just like, here's the input, here's a linear map, here's your output. There's some kind of a recursive update that happens to the input to get to the output. And there's this connection that have been made between the energy of a state and the probability of that state. So they're inversely related. So the low energy states are more probable, whereas high energy states are less probable. And so the output is generated through something called an energy descent, which is effectively maximizing likelihood. And then if you're like paying attention, you'll see that this network has recently made a lot of news because the 2024 Physics Nobel Prize was rewarded to John Hopfield along with Geoffrey Hinton. And it was for, like, John Hopfield's contribution was the specific Hopfield network. And those were the foundation of model machine learning and artificial neural networks. But getting back to associative memories and what they are, these are models that are parameterized with something called memories. So if you have, say, M memories denoted by xi's, and say memories are some vectors here, then your model parameters are also can be interpreted as memories. And you always associate an energy with the memory. And this is kind of a very general way of writing the energy. So the energy of a state V over here, given my memory, is dependent on the similarity between the state and the memory. This is what this S function is. Some kind of a nonlinear activation of that similarity. And then you add it over all the memories, and then you kind of apply a monotonic function like a log or something to scale it properly. So this is saying, given my model parameterized by memories, this is the energy of any state, any V. So then how do we use this model? Right? So the way to use this model, as I said, is that by connecting the energy to the probability. So with the assumption that the probability of the state V is proportional to like the exponent of the negative energy. So they're inversely proportional. So the log likelihood, the negative log likelihood of a state is proportional to the energy. So if you're minimizing the energy, you will be maximizing the log likelihood of a state. And you can use that intuition to think about how to convert an input to an output via energy descent. So we can start with some, if we have an input, say V, we seed the initial state with that input, and then we do a kind of a gradient descent, but on the energy function. So we are given my model parameters, which are the memories. And then you get to a fixed point, which is denoted by this, and that's kind of related to your output. And you can visualize this with kind of this figure on the right, where you can see like the red curve shows the energy landscape, and the blue balls are showing how some input is being modified through states to get to some kind of a fixed point. And a nice property of this model is that the fixed points tend to be something that's close to one of the memories, and the output of can be a function of this fixed point. And so if the fixed points are kind of connected to the memories themselves, then if we can pack in more memories, then we can have more fixed points. We can effectively have more fixed points. And when you have more fixed points, what you're doing is you're making your model more expressive. So you can have more different kinds of output for different inputs. So there is being able to have more local minima means you can potentially have a more expressive model. But having more memories means also adding more parameters to the model, right? So your model is becoming bigger and bigger. But this is like a video created by one of my co-authors, kind of visualizing how adding more memories adds more local minima to the energy landscape. So you can think of the energy landscape here being like a two-dimensional. Each red dot is our memory, and the arrows are showing which way you'll go from any part of the space based on your energy descent. So again, showing the video again, you can see like you started with 3 memories, and this is how your energy landscape looks like. You add a 4th one, 5th one, 6th one, they are kind of changing and making the function that you effectively have much more expressive. But it comes with a cost. Every added memory is now a new parameter in your model. So on this notion of how many memories you can put in, as I said, this expressivity of the model is related to how many local minima of the energy you can create. And one interesting connection is, and this is something you can look up, is that these models are very closely related to modern transformers. So they have like a close connection, but I'm not going to get into that connection right now. But in case you're curious, you can look it up. But the expressivity is related to something called the model capacity. And if I look at the energy function that I posed, wrote down earlier, if we make the f function, that nonlinear activation, just a quadratic function, you can show that the capacity of the memory is bounded by d, O of d. So it's something that at most d memories you can pack in. Anything more than that, you will not get that many local minima. Some of your local minimas will start merging together. And so you don't get the expressivity from added parameters there. But if you, and that was the classical Hopfield network, the one that John Hopfield came up with in late 70s, early 80s. Now, if you make the activation function like a polynomial with a degree greater than 2 or an exponential, your memory capacity grows accordingly. And these came out in like the 2016, and they have significantly more memory capacity, which is exciting. And these are called the modern Hopfield networks, or the dense associative memories. And with exponential activation, if we can get exponential number of local minima, this is an extremely expressive model. In fact, this is enough models to show universal approximation. So you can universally approximate any function if you have exponentially many local minima up to any desired accuracy. But remember, the number of memories we are throwing in is related to the model size. So effectively, this is saying that we need a model which has size which is exponential in like the dimensionality of the data, which is gigantic. Like if we have 100 dimensions, then this exponentially in 100 is already a pretty big model. And then we always have data which have higher dimensionality. Think of images which are like 32 by 32 by 3 and are low resolution images. But if you go high resolution, what dimensionality that the data has. So this is not, it's a good possibility, but this is not a tractable model size. And this is something that we address in this recent paper we have with my co-authors, Ben Hoover, Duanghong Chao, and Henrik Strobel, and Dmitry Krotov. And this is something we'll present at a recent conference next week, actually. And the main our main observation here is utilizing some ideas from Fourier analysis. We see that if we can replace this similarity computation followed by the activation with some kind of a dot product given some feature map. So we have some feature map, and then we have this relationship. What ends up happening is our life becomes much more easy, because we can write the energy function, which was initially written as this, and you can simplify it, and you end up with an energy function which only has this single parameter. And everything else is kind of, you don't have to keep all the memories. You can actually entangle the memories using the feature map and just keep a single, with just a single parameter. And this is something we called distributed representation dense associative memories. Whereas the original one, we can call it the memory representation. So we have to keep all the memories, and this is a distributed representation where we entangle the memories into a single representation. And again, my co-author created this nice video. This is showing the example for a very specific similarity function, which is the negative Euclidean, squared Euclidean distance, and the exponential activation. So where the activation function f is the exponential one, it's rapidly increasing. And this will show an example of a specific function feature map, which allows us to simplify the whole thing. So this is the original energy for this looks very much like the RBF kernel, the radial basis function kernel. And the distributed representation, we can do that simplification. And what you see on the bottom here are these Fourier features. So effectively, you can create a feature map which approximates the RBF kernel, and that allows us to entangle the memories and reduce the parameter, potentially reduce the parameter size. So just to highlight kind of the requirements, like how big does this feature map need to be? We can show that if the feature map is of this size, the y is the size of the feature map. This feature map is of this size. Then all these approximations are bounded. So there is, so you know that the approximation that I'm utilizing is not completely terrible. There's a bound that we can track. And so going from the original memory representation energy function to this distributed representation energy function, our number of parameters go down from m times d, where m was the number of memories we had, to d by epsilon square. So which if m is less than 1 by epsilon square, and we want the epsilon to be as small as possible, then we don't gain anything. But think of the scenarios where m is now in the modern Hopfield network setup, where it's polynomial in D or even exponential in D. In those scenarios, we have some hope that we can get better parameters, and that's the space that we want to pursue here with these models. And this is just some empirical evaluation, but you can look at the details more in the paper. But essentially, we show like the whole idea. We theoretically say how bad our approximation is, and it depends on a few factors. One, how big our random feature map is. Bigger is better, so that's kind of a given. But it also depends on how far or close we are from the memories themselves. Our energy approximation is very good when we are close to certain memories, but our energy approximation gets a little bit worse when we are far away from all the memories, which is kind of we don't know how problematic it would be for downstream tasks yet. So that's something that we're still looking at. But both the energy and the gradient of the energy we need to generate our output are pretty good when we are near the memories or somewhere near to the memories. And this is just another example where we essentially store these pictures as memories in our system, and then we input a cropped version of the picture. So the top row is showing the cropped version of the picture, and the bottom row is what the original modern Hopfill network or dense associative memory was able to reconstruct. So given the memories and the cropped input, it was able to fill in the pictures nicely. Our version also is able to more or less fill it in nicely. It's a little bit more noisy if you look closely, but for the most part, it is getting the shapes and forms correct. So it's visually close enough. So effectively, we showed a way of getting a better model size trade-off here, and for a large enough model, it can also like speed up inference and thus training, because training is just a repeated inference and loss calculation. And the mathematical tools that we use here were some kind of Fourier analysis based random features, and then some kind of theory from the kernel machines literature, if you're familiar with that. And of course, open questions remain, such as how to improve this trade-off of size and expressivity. Dense associative memories are kind of becoming popular now, but given the Nobel Prize news and all, and I think this application to more tasks and scaling to larger applications will get more support now. But when we were writing the paper, which was before the news, it wasn't as popular. So most people didn't really know much about this model or use it in the machine learning literature. But the other question is, could we use similar mathematical techniques to make existing gigantic models smaller or more cheaper or more computationally plausible? To me, that's a very important open question. But with that, I'll come to the last part of my talk, where I want to say, look at the data aspect. Like we were talking about how, if you look into how much data is used to train these large language models, and how much data is also being constantly collected to then use in these large language models, it's pretty enormous. And as you increase data size, you have to increase your model size, you have to increase your compute costs to train on such a size data. And the question is, can we get away with small amounts of data? And that's what's interesting to me. Like, can we train models of similar capability without having such a gigantic data requirement? So going back to this ARC problem that I had started with. So you see some examples, and you have to immediately identify what the notion is. And so, but one thing that you see is that colors denote shapes here. So anything of the same color and are connected are probably the same shape, same object in this picture. And then the problem is about manipulating objects. In this case, you are moving the above object down. Again, in this case, you are seeing, okay, but this notion remains the same. There is this notion of objects, like the same color and connected pieces denote an object. In the top examples, for example, there's only one object. In the bottom example, there are two objects. So this object are pieces that stand out to us when we're looking at it as humans. And then based on those objects, we have to manipulate it in a certain way. In this case, we have to find the center of the object and fill that in with the matching color. So that's the task here. But still, like, we are not looking at this picture as a long string and then trying to match every token in the string to everything else. We are actually composing the picture into composing it into smaller pieces. We are saying, okay, there's a background and then there's an object. We already disentangle that. And then we do object manipulation. This is an example, again, cleanup, right? So we again know which are the objects given the color and how they're close to each other in the image. and which are things which could be considered noise, and so we think about how would we complete this. So again, we extract out objects from the picture, and then we do manipulations of that object. And all these examples, like even though they are different skills themselves, they have some relationship, right? Like we have notions of color, we have notions of shape, we have notions of how we can use notions of color and shape to make them into objects, and then we know how to move an object as a whole. We don't move it pixel by pixel. We take the object in our head and we move it by ourselves as a whole. And so these are just more and more examples of that form. And so there's this what's known as a compositional structure, right? Like we are not solving the problem completely from pixel by pixel. We look at the picture, we extract objects, and then we extract maybe colors and location. Based on that, we make an object. Based on the object, we make then relative position and then manipulation. So there's this, we are composing things recursively. And then to see that more explicitly, we consider this problem setup. This is called list operations. And the task here is that you're given a sequence of this form where you have brackets, which are showing what the delimiters are for your operation. And then you have to operate on the list and get a final answer. And the way to solve it is you kind of find the smallest enclosing brackets, and then you solve that one. So in this case, the smallest ones are this max on 3, 2, 2, and the max is what? 2, 3. And then you have the min 8, 6, 2. What's the min? 2. So then you go up one more level, and then you have a new problem where you have to solve, you find the smallest enclosing brackets, which is the sum of 2, 2, 9, 3. It's actually sum mods because you want to keep answers between 0 and 9. But it's, so you have sum mod of 2, 2, 9, 3. What's the answer there? It's 6. So we solve that piece. And then we finally solve the largest enclosing brackets, which is the median of 7, 3, 8, 5, 6. And then we get to the final answer. So when we look at the initial problem, we don't solve it in one shot, right? Like we are looking at smaller pieces of it. We're composing answers of those smaller pieces, and we're building up the answers as we do that. And one way of saying it is that the meaning of the whole is the function of the meaning of the parts and of the way that they are syntactically combined. So this is an example just showing how to get to the final answer, we have to break things into smaller parts and recursively build up the answer. And this is a structure in this problem. This is also a structure in the ARC problems that I showed you. And I believe this is also a structure in almost all of language, right? Like when somebody says a long sentence, we don't process the long sentences one go, right? We break it up into smaller parts. We understand the meaning of the parts, and then we build that meaning up recursively to get to the final meaning of the full sentence. If somebody's asking you a long question, we don't look at the whole question in one go. We break it into parts, and then we solve piece by piece and build up the answer. And what that gives us is this ability to generalize with just few examples. And this is how, like, so look at the problem here. So we had the initial problem where we had to solve this string, and I told you how to solve the first string, right? So now if I replace the 3 with the 1, then I think anyone in the audience will be able to immediately solve this problem without any more examples, any more training data, right? We immediately know, okay, I replace 3 with 1. So the only thing that changes is how the max is, this enclosing max is going to, its output will change. So no, the output is no longer 3, it's going to be 2. And then subsequently, other parts will change a bit, like where we compute the median, the things change a bit, but again, the final answer does not change. And right part where we were operating on the min and the sum mod, that is completely untouched. So that has not changed at all. But doing this simple change, we can still solve the problem. In fact, if we do even a little bit bigger change where we swap the max and the min in closing brackets, right? Like we create a new example where I swap their positions. I think we can still solve this problem, right? Like it's very simple because we are still solving small pieces and building it up. So when we do that, we won't get thrown off the moment small pieces get swapped off. And that's something that we as humans can do pretty well, but it's not something that these large language models are trained to do well. They are just shown as many examples as they can show for these strings and hope that for a new example that they have not seen, they somehow can solve it. They effectively don't solve it up bottom up as we think is meaningful. There's also a whole literature of like polynomial equations and polynomial expressions and algebraic circuits, right? When we are learning these in like high school, we are learning how do we solve this. We think, okay, given an equation, we kind of build a syntax tree, and then we solve them, and we have different kinds of syntax trees, whether it has a certain depth, number of variables, what order of a polynomial it is. All these things we can think of. But once we understand something like a 2-depth syntax tree or 2-degree polynomial, it should not be very hard for us to understand or operate with 3-degree polynomials. Similarly, if we only learn to add even digits, right, then we should be able to add odd digits. The concepts remain the same. Or if we can take sums of products, we can then know how to do product of sums. These are things that we know because, again, in every case, we are building up smaller answers using what we know, solving smaller problems and building that up to solve the bigger problem. And similarly, if we know how to solve smaller algebraic equations, something that only has like 5 terms, then we can probably solve a polynomial equation with the same operators with 10 terms. Like we will build up small to big. Of course, if we throw in new operators you've never seen before, then that's different. But assuming that the operators remain the same, we can handle longer expressions. Similarly, we can kind of looking at, so what we figured out is that these algebraic equations or algebraic circuits are great candidates for testing for generalization. So this is an example where we can give a system 2 inputs, 2 polynomials, which are effectively the same. One is a factored form of the other, and ask it, can you figure out whether they are the same? And for it to be able to figure that out, it needs to probably do this building up from pieces, this composition, leveraging the compositional structure. It needs to be able to do that. Otherwise, chances of it being able to solve this is going to be, with few examples, it's going to be hard. We can also kind of create sequence to sequence tasks where we can ask a model to take a factored form and create an expanded form, or take an expanded form and create a factored form. Right? So these are hard problems, but for us to be able to do it, we did it when we were doing it as young kids in high school. We were doing it by solving smaller pieces and then building it up, like leveraging the compositional structure, which is what I think we need to do. And based on this kind of intuition, we kind of propose this way of evaluating AI systems, especially with algebraic circuits, because we think these are great candidates to generate a lot of data, to generate a lot of test samples, which are just enough different from the training data, We can evaluate different kinds of models with that for different tasks like classification, sequence to sequence. And I think these algebraic circuits should be part of any AI lifecycle because of the beautiful compositional structure they possess. And this is something that we discuss in this paper, which is under submission right now with my collaborators Takuya Ito, Murray Campbell, Leo Horesh, and Tim Klinger. But coming back to this compositional problem that I showed you, how you build up answers by solving smaller and smaller problems and going up the chain, you can write it out more mathematically as kind of talking about the meaning of the whole as a function of the meaning of the parts, where you have a meaning function that operates on subterms which are combined with some rule. And then you have a rule-dependent function which is equal to the rule-dependent function of the meanings of the parts themselves, meanings of the subterms. So the subterms are kind of, we get a meaning out of them and we can combine them back. So this effectively has a recursive structure, right? So, and in a way, we are applying that recursive structure when we are solving this problem. And what ends up happening is that when we are solving this problem, we are effectively building a computation graph, right? We have a, in this case, this graph just happens to be a tree, but we are building it up because we are solving small problems, getting the answer, using it to solve the upper level problem and getting the answer and then solving the next level and so on, kind of building up the solution. This is how kind of I would solve this problem, but how are models solving it? Like standard models from neural network literature, they take this as a string of tokens. You do some kind of token embeddings. You then throw it into some model. Could be like a convolution model where you convolve and pool and convolve and pool. Then you do a class prediction and then you figure out whether what's the answer. This is just one model. You could also use a recurrent model where you can do forward recurrence through the sequence or backward recurrence through the sequence. Again, use that to get a answer. But at the end of the day, even these models have a computation graph. It's a trace of how it's hierarchically composing the tokens in the sequence. And based on this intuition, we have a paper at AICTE this year, which kind of theoretically studies what it means to be a compositional function, what makes models compositional. And this is a much more theoretically dense paper, so I won't get too much into it. But the main idea is we kind of show that all models have this part, which you have like a token encoder. But the important part is this compositional DAG, or directed acyclic graph. And we kind of operate up that acyclic graph, directed acyclic graph, to get to our answer. And this setup kind of maps with the more non-formal definition of compositionality. We are building up the answer from by solving smaller parts of the bigger question. And we can show that recurrent models fit in this framework, convolutional models do fit in the framework, even transformers fit in this framework. But what's different between all these models is that they have a different notion of what we call compositional complexity. And it's tied to kind of the complexity of the directed acyclic graphs they induce. And some of them induce pretty simple acyclic graphs, so they have less complexity. And some of them introduce very complex graphs, so they have high complexity. And then the details of how we compute and these complexity, define and compute this complexity is in the paper. But this is just kind of showing that we can quantify the complexity of these existing models. But the main implications and insights are that we can actually now quantify complexity, compositionality, compositional complexity of these models. So we haven't done this yet, but we can potentially use that to regularize these models to make them less complex, just like we do like norm regularization to make them less complex in different ways. We can directly regularize compositional complexity. We can our analysis also answers certain questions, such as why transformers are why transformers are more expressive than recurrent models. And back in the day, when like maybe about 10 years ago, when vision was the rage, it was seen that max pooling happened to be a very critical operation, and we kind of give a theoretical reasoning for why that is the case. And another implication, and this is something that's ongoing work, is that based on the theory, we figure out a way to make small change to the transformer so that it can generalize better on compositional data. And this is an example. So we have 3 different tasks here. The first task, called missing duplicates, is essentially you're given 2 copies of the same binary string, but on the second copy, 1 bit is missing. 1 bit is missing, and you have to fill in that bit. You have to fill in that bit. Or you have the list operations that I showed earlier, or unequal pairs, where we are given a string and we have to count how many 0 1s are there versus how many 1 0s are there. And this is something that we can do like pretty easily, right? And we don't need like too much training data to be able to learn that. And in these plots, what the x-axis is corresponds to data and compute, like how much data we need to train the model. And the y-axis is tracking kind of the accuracy of the model on solving this problem. And the black line is the standard transformer, and the green and red lines are different variations of our transformer, where we kind of explicitly regularize the complexity of the transformer. And what we end up seeing is that we are getting to the same level of performance and thus expressivity as the standard transformer, but with significantly way less data. In some cases, we are almost like 5 to 10x. We need 5 to 10x less data to get to the same level of performance. And then these are compositional tasks. Like I give you a couple of examples. You can solve them very easily on a new unseen example, but models struggle, and we are able to make them generalize better with less data. So it is possible. Again, these are not giant large language models on like realistic problems. These are toy problems and toy models, but this is evidence. I see this as evidence that we can do better with less data. So our main contributions were like creating a formal quantification of compositionality, making precise connection between complexity and expressivity and generalization. So these are kind of theorems we have in the paper. The main mathematical tools that we used were combinatorics and stability analysis. So again, I like to highlight like these are the different mathematical tools that we needed to get to this point. And the open questions remain, like how do we incorporate this into current model? How do we create current models which take advantage of the fact that most of language is compositional? One of the challenges is that compositionality is kind of a discrete quantity, whereas we know how to learn well with like continuous optimization problems. And so that will be a challenge, and we'll have to figure out how to solve this mixed discrete continuous optimization efficiently. And finally, what would be best to think of new models which are inherently compositional. Like we don't have to make them compositional. They are compositional out of the box, and they are able to adjust depending on the need of the problem. But that's like a hard problem, but the hope is that if people are interested in this enough, somebody can figure it out. And so I want to conclude with a couple of slides on just like what I think is next. Right? Like to me, again, the top is the problem that I think we are solving right now to train these gigantic models. And the bottom is which I think is the right optimization problem to solve, to be able to learn to acquire skills. Not just learn a single skill, but learn to acquire new skills efficiently. But that's just my view, right? I think the question for the community is, what is the right problem to solve? Like, maybe what I had is not the right problem. Maybe they said some other right problem. So to me, that is an important question. What is the right problem? We can think about kind of similarities and differences between what is being solved and what we want to solve. Can we make the standard single level one that everybody's like, which is used to train these gigantic models? Can we add constraints to them to make them more like the one we want, where it's able to learn new skills? And can we make this problem easy to solve? Because if it's expensive and we are continuously doing it, that's just a waste of so much resources. Like, resources are infinite, and we are training these gigantic models, throwing so much compute at them. And at some point, we have to be more smart about how we spend our resources. And to me, mathematics is the right tool here. Like, we can find the right easy problem, we can solve it efficiently. Of course, I kind of talked about how we can generalize better in terms of skills with robust bi-level optimization, but that had some challenges that I mentioned earlier, and I'm just repeating them here. We were trying to address model size with associative memories. Again, there are still open questions there, but the hope is that similar mathematical techniques can help us make more computationally plausible models. And again, I think compositionality is the key to reduce our data requirements. But compositionality comes with its own issues, so we have to be able to leverage compositionality while still having efficient training algorithms, and that's one of the main open questions. And finally, like, if I have convinced you that this is an interesting problem, even if it's not the right problem, then my final message to you all is, like, how can we use mathematics to find the right problem to solve and solve it without prohibitive costs? Because, at least in my opinion, what we are doing right now is not scalable. It's the cost of training these models are just too prohibitive. And even what we train right now is just, we are doing it, but we are not paying the future costs of what we are doing right now. And I think we need to think about, on paper, what is the right problem to solve before we throw giant amounts of compute to try to solve those problems. And with that, I want to thank you for your time, and I want to thank Professor Mishra for giving me this opportunity to speak here. This is my email. You can find more about my work here. I'm not very active on social media, but I just joined Blue Sky, so if you're on there, feel free to connect with me. And with that, I want to thank you all.
Thank you, Dr. Parikshit, for nice informative sessions on critical role of fundamental mathematical tools in path AGI. So, I mean, now I would like to see if the participant would like to discuss with you and ask some questions. The floor is open for you.
Hello, sir. Sir, like, hello.
Hi.
Hello.
Yeah, you are audible.
Yeah. Sir, I would like to thank for giving me this opportunity. Sir, your session was super cool. It was super cool. Sorry for asking a question which is not technically that advanced. As a student, you made me a student in a session, and how come you made such a wonderful PPT, sir? Are you using any tool? It was really fascinating. The entire session, we were there with the PPT. So many of us, I think so. That to Max.
No, sorry, I'm not like a specialist at this. I think the tooling was just standard Microsoft PowerPoint. I'm not fancy about that. I think I just wanted to make sure that the story and to me, I want to kind of get people interested in the problem itself. Like, this is a real problem that we are facing right now, and I think we have the opportunity, especially for the newer generation, to solve this in a smarter way than what we are doing right now.
That PPT made us to get into that topic. Thank you.
Thank you very much for your kind words.
Good evening, sir.
Good evening.
Sir, basically we are proposing the mathematical tools. So is there any real implementation or simulation tools are available, so that who are the newcomers in the field of research can try these mathematical models and verify the logics what they are developing. Or only we are able. There is no simulation tools are available in to verify these mathematical models.
I mean, so all like we do both. We do the theory part, but we are also implementing. And the nice thing about the time we are in now is that we have a lot of nice tooling. Like all the simulations that I did show are in open source tools like PyTorch, or TensorFlow, or NumPy and such. So everything is built on those things. And again, you'll have to look into the papers themselves to see how we implement many of these mathematical concepts or algorithms. But they are all like open source tools that are like built on like open source tools like PyTorch or NumPy. I don't know if that helped answer the question.
Good evening, sir. A very nice presentation. You had spent quite a lot of time explaining the importance of bottom-up approach. So that was really nice. So how important it is to understand the base cases you were about to tell you. Maybe how important it is to learn the base cases and to go for generalization. For example, you have used factorization as the example here, polynomial factorization. For example, if you take RSA, basic factorization is still pending. You can't factorize a large number as a product of 2 times. It doesn't matter what model you train or what, it's just an open problem. So it was very nice that you are tackling the bottom-up case. And of course, can you, because students always they go for, say, optimizer available, atom optimizer available, they'll blindly use it. So how important is the base case? If you are able to tell few lines, it will be helpful. Thank you.
Yeah, no, I mean this is a very hard question, to be honest. But that's the motivation for kind of looking at the compositional structure. That if we can teach, like again, the overall factorization problem is a hard problem. Like I don't think models can solve it. We humans can't solve it. But even simple factorizations are hard for models, and so we have to train models in a way that they know that not only do they know how to solve the base cases, which is very important. If you can't solve the base cases, you can't solve the bigger problem. So that's critical. But you also have to know how to extract small, if I understand your question correctly, like
yes, sir.
Extracting small base cases from the bigger problem and then solving that, and then applying that answer recursively up your solution,
yes,
is equally important. Otherwise, we will only be able to solve base cases and not know how to solve bigger problems. So this identification and using that solution in the right place is also critical, very critical. Otherwise, we'll be stuck in just solving base cases. But without the right base case, of course, we can't solve the bigger problems because the error will propagate very quickly.
Yes, sir. Thank you, sir. Thank you.
Thank you for your question. I see one other hand raised if they want to come off mute and ask a question. If that's okay, Professor Mishra, take one more question. Otherwise, we can.
Anybody? I mean, Dr. Arul Raj, if you want to ask any question, or okay. Yeah, just I mean, fine. I think if anybody wanted to ask question or an interaction, I mean, Dr. Parikshit have already shared his mail ID. You would have you can reach out to him and you can interact in case any queries you have. So once again, because I would like one question. Bi-level optimizations what you have used in the algorithm. When I was going through that the algorithm, I would say I just want to know that how this you say there is in the, suppose in the gradient descent, there is no role of the second order part, right? I mean is it the bi-level case? It has influence. How it is in the algorithm, it isn't visible. So
yeah, so the algorithm I shared was very high level. I did not put in the information.
Correct, yeah.
The main detail, if you, as I pointed to some of those tutorials, the main detail is, if you look into it, that in the bi-level structure, when you're taking the gradient, you're solving the lower level problem. It's a simple optimization problem. But for the upper level, what happens is, if you want to take the gradient with respect to the upper level variable, a simple gradient is just the partial gradient. If you want to take the full gradient, you actually have to take the gradient through the solution of this lower level problem, because the lower level problem depends on the upper level variable, right? And so the solution depends on that. So you have to take a partial through an optimum, and that you have to utilize something called the implicit function theorem. And so that when you compute the true total gradient of the upper level variable, it will come out as the Jacobian of the lower level function with respect to both the upper and lower level variable, and the Hessian inverse of the lower level variable. And without that right gradient, the upper level there's no guarantee for it to converge. Maybe for your problem it will work out, but in general it won't. There are easy, simple cases where you can show that it won't converge. So you have to make use of this implicit function theorem to get the gradient, and the gradient is more complicated. Of course, you can approximate the Hessian and the Jacob, or try to approximate it. And that's what people do in practical implementations. Nobody's computing the full Hessian. You can approximate and use different kind of techniques, whether it's conjugate gradient, or whether it's something called the von Neumann series. But again, these are mathematical tools that are used to solve this other optimization algorithm. So they're all
conjugate gradient can also be used for the computing. I mean, the respect to the Hessian.
Yeah, the Hessian inverse vector computation can be approximated with conjugate gradient, right?
And one more, just looking at most of the algorithms, like any stopping criteria, is there any specific about one can discuss about stopping criteria or something, or just you have some tolerance is there, that's all enough?
Yeah. So usually it's tolerance, right? So some kind of convergence tolerance, or you run out of compute budget, right?
Because sometimes what happens, for example, I say about conjugate gradient. For example, conjugate gradient, what it does is actually, it actually minimizes the error norm, okay, but it doesn't minimize the residual. But in practice, when you do the computations, you always can see the residual, but you cannot see the error.
Yeah.
Right. So for that, when you put the stopping criteria over the residual, but error already converged, but you are doing some additional computation for the residual. That generally happens. So that's why finding a right stopping criteria which can save our time instead of doing additional unnecessary cross, because sometimes because the residual is not actually minimizing at each step of the conjugate gradient. So sometimes it's not minimizing, it's just stagnant there someplace. But our computation will go on, running for a long time. But that if you see the error already converged.
So that is a challenging question, right? And that is, for what you're raising is a challenging question just for conjugate gradient. But I think in the bi-level solution, conjugate gradient is a minor subroutine in the bigger problem. So that just highlights how complex bi-level optimization is. So you're raising a very good point that it's challenging. So just conjugate gradient by itself is challenging. And when you have to invoke it repeatedly, it becomes more challenging. And that's why the goal is to kind of come up with more optimization algorithms, which either don't need like you can think of an algorithm which says, okay, I can guarantee bi-level convergence where you only do one step of conjugate gradient every iteration, right? If we can show that it can, like with certain correction, you track corrections or you handle that, then that would be a novel, very scalable algorithm, right? And that's what we want to go towards.
like restart GM, just do like that, no? Like
Yeah,
minimum number of iterations. But the inner iteration will be some kind of fixed inner iteration. Like that, you are talking about one iteration of CG can be fine.
yeah, exactly. Because in the initial stages of the optimization, we don't need high accuracy CG solution, right?
Yeah. Okay.
Because,
Yeah.
but yeah. Okay. Yeah. Thank you for your question again.
Thank you. So that's all. I mean, we actually the big thing is that multiple times Dr. Parikshit asked me to how to simplify the talk, because actually the subject is really complex and more the technical things, and to the general audience presenting is not so. I mean, it's really challenging. So, but actually, our curiosity is that how the people are working now in a IBM and the current trend, how the things are going, and so people can get an idea how the current trend is going in this machine learning. So they may be interested to collaborate and to work with the audience. So that's the purpose that I say that you can present of your work. So that's what he has done very nice job, and a lot of open problems there which can be the audience can take that challenges. Thank you, Dr. Parikshit. So I mean, with this great knowledge share with the participants.
No, thank you for organizing this amazing workshop and also giving me this opportunity to speak here. It's and for the audience to listen to me. It's I appreciate the opportunity. Thank you, Professor Mishra.
Thank you. With this, we'll close the sessions and we'll wait for 4 minutes, and then we'll start the because it's the last session, so we'll start our feedback session, and with next followed by the test for the program. So we'll wait for 4 minutes, then we'll start the closing sessions gradually. Thank you.
Thank you very much. I think I'm going to drop off here. Thank you.
Yeah. Thanks. So in 4 minutes, around 7:15, we'll come back. Just 3 minutes now. 7:15 we'll come back, and we'll have a. Please, all of you, please present and be present here. Before we start the online exam, let us have participants' feedback. Let me ask the participant to give their feedback regarding the workshop. I request who is interested, please unmute yourself, turn on your videos and introduce yourself and share your feedback regarding the workshop. You please take 2 to 3 minutes to share your feedback so that the other participants will get chance to say something. So I'll start, I'll open the floor for you. I mean, you can please unmute yourself and turn your videos and introduce yourself before saying, say something about the WhatsApp. And any positive, negative, all kind of feedback will be helpful for us. So that you can improvise the things, I mean, next time when we will do again.
Hello, sir. Hi.
Yeah. Video.
I'm Dr. P.S. Banerjee. I'm a PhD in Natural Language Processing from NIT Durgapur under Vishwacharya PhD Fellowship. I specifically joined this program to have some more better insights. And to the utter surprise of mine, Dr. Mishra, the kind of people that, the kind of speakers that you have amalgamated or gathered at one place was just fantastic and fabulous. Specifically, Dana ma'am and currently this Parikshit Saab and rest all, everybody was just awesome and fantastic. I got some, I mean, earlier it was like being even at NIT Durgapur or IIT Kharagpur, it was a very different perspective. And now here, what actually is happening in the industry level, it's terrifically different. It was really good to be here and wonderful experience. Thank you so very much. Thank you.
Thank you, Partha. Thank you. Thank you.
Hello, sir.
Yeah.
Good evening, sir. I am Baninanda Acharya. I am Baninanda Acharya from Odisha, Cuttack. I joined this sixth session and I gained a lot of information from this session. I think it will still help me in my future. Thank you, sir.
Thank you.
Good evening, sir.
Yeah.
Sir, myself, KB Srinivas from Manipal Institute of Technology, Manipal.
Yes, please. Yeah.
Yes. So this from Department of Mathematics.
Yes, Srinivas, please go ahead. Yeah.
Yeah. So what I felt was this workshop. It was really wonderful. Highly intellectual people from industry and academia. I have come for this.
Excuse me, Banindita Acharya, please can you mute yourself? Please mute yourself. Yeah, thank you.
Thank you, sir. Highly intellectual people who are actually working in industry on top things. They have come and presented here. It was really wonderful. And the speakers, I believe, they took extra efforts to start from the very basic level. And they have worked out physically things on the screen and made the things simple from what they call as bottom-up approach. And from very simple problems, they went to NP complete, NP hard problems, and they provided some approximate solutions. It was very, very nice to see that, and it will definitely help us to motivate students. And I also want to thank Dr. Nachiketa and Dr. Sanjeev Kumar sirs. It is not easy to organize event of this level. I am sure they have also huge. They are also huge. They have also huge contributions they may be having in the field, and it would have been nice if one of them could have given a talk also. So hopefully somewhere in the future they'll do that. It is not at all easy to conduct workshop of this level. I congratulate them, and I also congratulate IITDM, and I want to thank AICTE for giving us this opportunity. Thank you very much, sir.
Good evening, sir.
Yeah.
Good evening, sir.
Yes, you can switch on your video and then you can introduce yourself.
I'm Dr. Sadanjali Naik. I'm from Bhubaneswar, Odisha. I'm from this group of institution. And the intersession is really very informative. And the experts from various domains, they have explained in such a simplest way that will not only help us improve our knowledge, that also guide us in using that in a research perspective. And thank you all the Nachiket sir and Sanjeev sir for their continuous effort, and till end they are supporting and they're coordinating us. It's really very, we learned a lot of things from it. Thank you, sir, for the session and for giving us such nice experience and nice knowledge that will help us a lot in ahead in improving our academic pressures also. Thank you, sir, for this informative. Really, it's amazing, and the coordination and the experts from various domains, the way they're explaining, it gives us a lot of. So we learn a lot of things to improve, to include that methods in our day-to-day teaching method, teaching life. So it's thank you so much, sir.
Thank you, Sadanjali.
Good evening, everyone. I'm Lakshmi Rupa.
Can you switch on the video, please? Yeah, good.
Yes, sir. Good evening, everyone. I'm Lakshmi Rupa. Till this July 2024, I was working as software engineer, a web application developer to be exact. I recently joined the Academia Fraternity, and till this particular point, I was very much confused about what I should do. From the beginning, from my childhood onwards, I have been dreaming of coming into teaching profession. I have to do my ME, Masters, then PhD. I have to do something. I have to come into teaching profession. This is what I was going into. But maybe I don't know. But the fate. I went into software direction, software IT industry direction, and for the past 10 years, I have been there. Now that I have come into the academic profession, and again the AICTE or UGC rules dictates that PhD is compulsion. I never had a particular pinpointed focus of research, how I should go, where I should go, what topic I should do. Every time I come up with some thoughts, it ends in a dead end. It ends in what should be the next thing I have to do, what is the next future of this particular point I'm going to do. So I really thank ATAL and Dr. Nachiket Mishra ji and Dr. Sanjay, everyone who have been involved in this particular session to actually come and organize this 6-day program. Now that I have actually attended this program, I know now what or where, in what direction I have to go now, from what point or the focused research where I have to take it from, or what point I have to take any from any particular research. So I thank everyone, one of the organizers, and a special thanks goes to all the speakers who have been participating in this particular 6-day program. They have taken out so much of their time from their busy lives. I really thank each and every one of the speaker who has come down to actually give us their time and show what actually has been going on in the current time, and everything what researchers are doing actually, and how the papers are being presented, or Dr. Saswati Dana, Dr. Parikshit, Dr. Srinivasan, every one of them, really a big thanks to you all. And Dr. Nachiket, and I really appreciate your time and effort for this, sir. Thank you so much. Thank you, one and all. I hope all the best for everyone in their future endeavors. Bye-bye.
Thank you.
Good evening, sir.
Yeah. Jyotiranjan, can you on your switch on a video? Yeah. Please introduce yourself. And, yeah.
Good evening, sir. I am Jyotiranjan Naik from Cuttack, Odisha. Currently, I am at Dreams University. I'd like to thank all speakers and the entire team of IIIT Kancheepuram who has arranged this 6 days FDP program, which was very interactive, and I will extract my knowledge from the 6 days FDP. So thank you very much to all.
Thank you. Thank you. Thank you, Jyotiranjan.
Good evening, sir. I am Dr. Suprita from Manipal Institute of Technology, Manipal. So it's very informative sessions which I attended. All the sessions are very informative. Thank you. So I will express my deepest gratitude to organizers as well as the session faculties. Thank you. Thank you.
Good evening, sir.
Thank you. Thank you, Suprita. Yeah.
Good evening, sir. I'm Mercy from St. Joseph's College, Trichy. I would like to express my sincere appreciation to all the organizers, speakers, who contributed to the success of this FDP. The sessions were not only informative, but also incredibly inspiring, providing us with valuable tools and knowledge to enhance our teaching practices and academic growth. So I'm grateful for the chance to expand my skills, and I'm excited to apply these insights in my own professional journey. Thank you, sir. Thank you for making this experience so impactful.
Thank you, Mercy. Okay, so fine then.
Good evening, sir.
Yes.
I am Niharika Dalai from Cuttack. I am working as an assistant professor.
You can switch on the video.
Yes, sir. Yes, sir. Good evening, sir. I am Niharika Dalai. I am working as an assistant professor in Dreams University. Actually, I would like to thanks all the IIITDM team organizers, and actually this session is very much informative. All the experts were very much knowledgeable and well experienced. I'm very much glad to be a part of this FDP. I would like to join more like this FDP. And in the last, I would like to thanks each and everyone of the IIITDM. Thank you. Thank you, sir.
Sir, good evening. Good evening to all. I am Perinaigi, VIT Bhopal, Associate Professor from VIT Bhopal University, Bhopal. So it was a really informative session, and mainly the session with sensor data generative. That session was very useful for me because I'm a researcher who's concentrating on sensor data and generative AI. That session was very useful. And other sessions, most of the sessions was handled by the industrial experts. That was very useful. And thanks for the organizing team for their timely communication for each and every small changes in the sessions and other things. It was really it was useful. Thank you, sir.
Thank you, madam.
Good evening, sir. This is Dr. Bhavani Shankar Mohanty, working as assistant professor from Central University, Tamilnadu, Department of Statistics and Applied Mathematics. And as a statistician, I have interest on AI and data science. And when I joined, and I really enjoyed all the sessions. All the sessions are very good. And really, I thank to Nachiketa sir and Sanjit sir for this accommodative job. Thank you, sir.
Thank you very much.
Very good evening, sir. This is Dr. Maithili from SRM University, Ramapuram. So I thank the organizers for giving us this opportunity, and also ATAL program for giving us this opportunity. As we are from computer science background, we know certain CS fundamental concepts, but mathematically we are not aware where to use and how to do the mathematical modeling in the research of this particular area of AI and data science. So we thank Mishra sir and Sandeep sir for organizing such a wonderful activity, which is very professionally organized. All the sessions where the flow of session topics are actually that flow is very continual, sequentially designed. So starts from the model selection, that is the problem objective, that means applications of these domains, and which is ended up with the mathematical modeling, so which was very useful. And the speakers were all from the top premier industries and also from academia. Thank you once again, Mishra sir and other coordinator, and also AICTE for giving us this opportunity. Thank you, sir.
Thank you. Thank you, madam.
I am Debismita Sahu from Dreams Polytechnic, Odisha. And thank you so much, Nachiketa sir, for organizing such type of very intelligent, excellent session. And we got to know various type of algorithms and its applications, and we got to know various type of problems also. And we found it very helpful. And me and my colleagues have joined the program from last days. And we really found it very helpful, and we expect such type of programs in future also from IIIT Kancheepuram. Thank you so much, sir.
Thank you, Debasmita.
Good evening, sir.
Yeah.
I am Swarupa, sir, working as an assistant professor in Mary Lakshman Reddy College of Institute and Technology. And thank you for Parikshit sir and Srinivas sir, who give the wonderful information about the NP hard and NP complete programs, sir. And thanks for all the speakers who gave excellent information about all these 6 days. And thank you so much, sir.
Thank you. Madam, you can mute yourself now. Thank you. Any other participants can please?
Yeah, good evening, sir.
Yeah.
This
Please
is
switch on your
Dr. K.
video.
Dharmarajan. This is Dr. K. Dharmarajan, working as a professor, Department of Information Technology, Wales University. First of all, I would like to congratulate all the organizing committee. Each and every updates you can share through the WhatsApp. Another thing, your video presentation. Another thing, each and every notification we have to receive the frequently. Okay. Another thing, the session it is very useful, and then more we have gathering the lot of knowledge from your end. Okay. So I would like to sincere thanks for all the organizing committee for this wonderful session. Okay, thank you, one and all. Thank you, sir.
Kindly switch on your videos if anybody want to say, please.
Good evening, sir. I am Krishna Chandra, a postdoctoral fellow from IIT Gandhinagar. The program was highly informative, with experts from renowned organizations like ISRO and IBM. And the knowledge on the latest topic on ChatGPT was very informative. And thank you, Nachiket sir, for organizing such an informative session. Thank you, sir.
Thank you, Krishna. Hope no, anybody want to say? Yeah. Yes, please.
For giving this wonderful opportunity to introduce myself. I am Samita Rauter from Dream. I am native to Kota, Odisha. I used to work in this AIISc program, and throughout this FDP, I learned lots of valuable skills, which is really helpful in our academic career. Even I want to do the PhD in future. So this is really helpful. Thank you. Thank you for this wonderful opportunity. Thank you.
Thank you, Susmita. Thank you.
Sir, can we start with the test now?
Yeah, yeah. So if anybody is still there, because we don't want to, I mean, deny anyone, but if all has given their feedback, I mean, we can start. But still, I'll give anybody still want to say something.
Dr. Nachiket, just a suggestion, please, or a request from me. It would be very helpful if you can give a consolidated list of the speakers and their contact details, so that if anyone wants to pursue their further research or anything with any of them who have been here for giving us sessions, it would be, and it would be helpful to me as well. So thank you.
Basically, academic, those are researchers, they have their home page. You can always read them out. So there is no difficulty. For industrial people, only the difficulty is there. So for them, I can share the email IDs. And particularly for the applied materials, Professor Dr. Senthil Kumar, who he said that you can contact through their LinkedIn profile. He will be reachable there. So these are the things I would like to tell. But those are interested to share the email ID, I will share there.
Thank you, sir.
Thank you. Okay, so I hope everybody has expressed their I mean, I'm kind of the feeling and about this program and how much they are benefited, etc. So my purpose was just I'll say one word, that my purpose was that even though most of the participants are engineers and computer science background, so sometimes we the computer science, I am also teaching computer science students here, and design students, mechanical, electronics. So most of the time I found their lack of interest in mathematical concepts. And then I say them that you can check the people who are working in industry, and so they are not, they cannot escape mathematics if they want to really give something valuable to the company. Okay, so that is, you cannot escape. So that is the reason that the experts I have selected, they have very good depth knowledge about all the kind of models, whatever they're using, and they are mathematical and everything they know. That is why this is the purpose. I mean, this is the hope it's fulfilled. Anupam, you want to say something? Your mic is on. If you don't want to say, you can just mute yourself. And now we will have the exam. This total to 30 marks questions are here. 45 minutes you will get. In the chat window, I will share the exam Google form link, and you have to fill some details like registered email ID. Please don't forget those, very carefully. So that's why just don't hurriedly go to the link and just fill that. That's what my intention. Just you registered email, which you have registered using ATAL portal, that email ID you can put there. You may be joining with Gmail, fine. But the kind of, I mean, the particular mail ID you have registered, that you can put there. Registered name, exactly same in the ATAL portal. Mobile number which has been registered to ATAL, that mobile number. Before starting exam, you just fill these forms. Okay. You have to score minimum 70% to eligible to certificate as per the AICTE norm and regulations. So answer properly. It takes sufficient time to think the question and answer. Sometimes question may be very easy, may not, you should not think in critical way. There is no negative marking. Okay. Once the exam is over, please submit your Google form. Okay, don't leave it just because of you have filled everything. You have to submit, then only we can get the answer. Because sometimes I have found, so even joining the program itself, people have not put it out. They didn't add the program, but they mail me that we have already registered. Similar sense, we should not have the same problem. You have to submit, then only the will get your answers. Okay. After 45 minutes, I will stop the collecting the response from the participants. Once the exam will over, please be here in the link for the valedictory session. Please don't leave immediately. And once you complete your exam, you can chat box. You can see that you have submitted the answer, so that I can verify. That is what the entire brief of this examination. So I will request you. Okay, fine. So then I will just request you to be attentive, and I'm just sharing the link, and you can, from that moment onwards, I will just count 45 minutes. So all of you, please, very cool to be answered. Things are very simple. I mean, score will send by late evening. We'll send the score, not a problem. Okay, so please answer. Please have this link, and your time starts now, 7:43. So exactly 45 minutes. I'll just wait for you, your answers.
So the chat window is not opening.
Maybe yours, actually, because maybe your network is slow. That's the reason.
Okay. Can you share the link in mail, sir? It's not possible.
And WhatsApp group, you are there, right?
Yes, sir.
Okay, I can share that. Yeah.
Nachiketa sir, shall we put doctor or something prefixes above before the name, or shall we keep it simple?
Yeah, may not required. Just because name will be fine. If you have put it doctor in the hotel or portal, it's fine. Anything is fine. That doesn't matter.
Thank you so much.
Hello, Nachiketa sir.
Yes, yes, please. Okay.
Sir, multi answers are allowed, or only one answer is?
All are one answer only.
One answer only. Okay. Thank you.
So there are two links. Both are same, right?
Yeah, they are same actually. Some people have joined late, so that's why I have said.
Okay. Now that I have submitted my response, what can I do next, sir?
You can wait for the validity. That will be great help for me. Because validity will be after 8:30.
Oh, okay.
We have 5 minutes more, and then we can start the validatory function. We have 5 minutes more.
Sir, how about the feedback, sir? Feedback, where to do?
Feedback at the portal. So we need some time to update the attendance. So you wait for Monday, Tuesday.
Okay, sir.
Tuesday, most probably Tuesday.
Thank you,
Okay.
sir. Thank you, sir.
Yeah, yeah. Then you can did the feedback at the portal itself.
Sir, do we get notified about the feedback link being open?
You have notified already?
No, I'm asking if the feedback portal, if it is open in the.
Yeah, yeah. We will inform you through WhatsApp group and all. Okay.
Okay, sir. Thank you.
Once the attendance will be entered there, then I will inform you.
Okay.
Sir, we should wait or we have to left, sir?
Please wait for some time. We will have a validatory function, very short. Please just wait. Your presence is very important for the validatory function. Okay, so the time up. So now we can stop the test. So welcome to all to this validatory function. A very good evening to everyone present here in this online validatory function of AICTE ATAL sponsored faculty development program on future perspective of AI and data sciences, algorithm and applications, which is jointly organized by Department of Science, Humanities and Department of Computer Science Engineering, Indian Institute of Information Technology Design and Manufacturing, Kancheepuram, Chennai. Before proceeding further, let me give a brief report about this FDP. 200 plus participants have registered for this FDP. Our participants are genuinely dedicatedly attended all the 13 sessions, span across all the 6 days from evening 6 p.m. till 9 p.m., including Saturday having 3 sessions of test and everything. They have a lot of patience to attend all the sessions. I mean, great. I mean, very much thankful to you all. The technical sessions are conducted by 3 faculty members of reputed technical institutions. 10 industry experts also delivered talk during the FDP, out of which 2 are from foreign countries. Among 13 experts, we have 2 speakers from overseas, 1 faculty member at Pennsylvania State University, US. Other one is from industry, that is principal research scientist, IBM, US, Dr. Parikshit Ram. We tried to accommodate all the important aspects of AI and data sciences like large language model and interplay of edge computing and machine learning, graph neural network, federated learning, reinforcement learning, mathematics and statistics for machine learning, data generation, sustainable AI for energy efficient algorithm, AI for semiconductors design and manufacturing, optimization techniques in machine learning, AI in real world applications, MILP during the FDP. There are many other things we have left in this piece, so the multiple things have been covered there. As per AICTE guideline, 80% attendance is mandatory and 70% mark is mandatory for getting the certificate. I'm happy to inform that all of you, I mean, most of the many participants have scored more than 80% attendance and few participants have 100% attendance. I'm sure many will get score good in mark, I mean, the good mark in exam, and definitely will get the certificate, many of you. So now we'll just discuss about those who have many people have involved to make the this event successful. Now it's time to give vote of thanks to them. It's my proud privilege to propose a vote of thanks for today's validatory session. I would like to thank our Honorable Director, sir, and all Dean, Registrar, faculty members, staff members, and the kind support throughout the program. So multiple stages they have helped us and to make the things possible. I take the opportunity to express my heartfelt thanks to all the resource persons who delivered talks during this FDP. Also, I thank all the participants who are the key members of the entire event for attending all sessions during the FDP. Without you participants, it is impossible to make such a good event. So basically, when we see a large number of participants are there, the energy is double, both the participants and as well as for the speakers. The speakers are, when I have seen most of the speakers that we have attended multiple FDP, but such a large audience we have never seen. So they are also very much encouraged while giving their talk, and they are eager to interact with you. That is the things we have observed here. Last but not least, I would like to thank AICTE officials multiple time we reach to them for multiple concerns, especially when I mean with the one of the eminent speaker, Professor Sivaram Ambikasaran, who is a PhD from Stanford, and he was multiple places before, like New York University as professor and professor in Tata Institute of Fundamental Research, and then IISc Bangalore. Because of his home is in Chennai, so he became now professor in data science in IIT Madras. I was thinking that he is most, one of the most technical speaker in data science. He was unable to attend because of his health problem. So we convey this difficulty that unable to attend this talk. So AICTE people have accommodated that to how to proceed with that and how to add how to replace the speaker with another speaker. So, and also Dr. Saswati agreed to be the speaker for the second time. Those are all possible because of the AICTE officials. They have very instant respond to the mail, and anytime any queries we send, just 1 minute or maximum 2 minutes to get reply. I mean, I have received the approval of the alternate speaker night 2 p.m. That 2 a.m. That is what I'm surprised. I mean, even I am little delayed to check the mail. I check at morning 5 o'clock instead of the mail received at 2 p.m. 2 a.m. That's one good thing that about AICTE and the ATAL group. Thanks to them all. Thank you one and all for joining this validity program. With this, we are going to close this event. And I mean, great emotions to connect with all the participants here. They have already connected too much. I mean, they have actively participate and interact with the external experts. And another thing, just one last word, I would like to say that there are many research scholars and our lab members. Those are here. They each time they did a very good hard work. I mean, to make it facilitated. We are not able to do this work without those our students. They have effectively in the future work also they will be coordinated. So these are the great support from them. With that, we can close the validity program and close the session, and we declare the closing of the event. Yeah, certificate. So kindly remember that. So because it's Saturday, so we little adjusted. So we need a one break, Sunday break. Monday we will upload the. I mean the first duty is to upload the attendance. Next followed by the marks, and it will possible in Tuesday. Maybe end of the Monday or Tuesday it will be possible. It's a huge task because the participant also large number, and for all the 6 days we have to enter there. So you please bear with us for Monday at least, end of the Monday. So Tuesday, by mid of the Tuesday and at the Tuesday end, definitely we get something. So with that thing, I mean, once the feedback, once the attendance will be entered, we will inform you, and you can also give your feedback at the portal. So thank you all. Thank you very much. I mean, if you score less percent, definitely we cannot help. These are all, I mean, computer generated data information, so we cannot fabricate them. I mean, so in fact, we have taken care to make the questions of some general level so that people can score well. If you cannot score, we are really helpless, and we don't want to be. I mean, to make any such kind of things to that AICTE will be blame us. So we should follow the rule of AICTE ATAL guidelines. So hope you can cooperate with that. Thank you all very much.
Thank you so much, sir.
Thank you.
Thank you so much, sir.
Thank you, sir.
Thank you so much, sir.
Thank you, sir. Thank you very much. Thank you, sir. Thank you, sir.
Thank you.
Thank you, sir. Thank you very much, sir.
Thank you. Thank you very much.
Thank you all. Have a good night.
Good night.
Have a great weekend.
Thank you, sir.
Thank you. Thank you.
Thank you so much, sir.
Thank
Good night.
you. Good night. Good night.
Thank you so much, sir.
Thank you, sir.
Thank you. Thank you, sir. Thank you.
Thank you so much, sir.
Thank you. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you so much, sir. It was a
Thank you.
nice ATAL FDP program. Thank you.
Thank you.